Imagine you're standing outside on a clear night, somewhere far from city lights, and you look up. The stars are where you expect them. The moon is doing its usual thing. The world feels stable, ancient, reliable. The ground under your feet feels permanent. And somewhere in your pocket or on your wrist, or built into whatever device you're using to listen to this right now, there is a compass or a GPS chip that works like one pointing north. Always north. Steady, dependable, invisible. Now imagine that compass, slowly, over years and then decades and then centuries, starts to drift. Not a little. Not the kind of drift you'd correct for on a hiking trail. It drifts and wanders and weakens, until one day the needle just spins. Because north has stopped being a thing. Because the invisible shield wrapped around the entire planet, the thing that makes that compass work, the thing that deflects solar radiation and keeps the atmosphere from being slowly stripped away into space, has nearly collapsed. Not gone, but almost down to maybe 5 or 10% of what it normally is. Fractured into patches and fragments, scattered, unreliable, confused. That actually happened. About 41,000 years ago, Earth's magnetic field went through something scientists call the Laschamps Excursion. For somewhere between a few hundred and a few thousand years, the field weakened dramatically, and the magnetic poles didn't just shift, they nearly inverted, then lurched back again, never completing a full reversal, but wandering far enough and weakening enough that the sky above this planet would have looked genuinely alien. Auroras possibly visible from the equator. Cosmic radiation raining through the atmosphere in ways that don't happen today. An invisible part of our world nearly gone. And here's the part that keeps scientists asking questions. This happened right in the middle of one of the most important and turbulent periods in human prehistory. Neanderthals were still alive. Modern humans were pushing out of Africa and into new territory. The planet was locked in an ice age. Cave paintings were beginning to appear for the first time. Woolly mammoths and cave bears and creatures we barely have names for were roaming a world that looked nothing like ours. And during all of this, the planet's magnetic umbrella was flickering like a light about to go out. Tonight, we're going to explore what actually happened during the Laschamps Excursion. What the magnetic field does and why it matters. How scientists found the evidence for an event that left no written record and no human witness who could tell us about it. What the weakened field might have meant for the atmosphere, for the climate, for the animals navigating a suddenly scrambled world, and whether, just maybe, it touched the lives of the people who were alive at the time. The ones who painted on cave walls and buried their dead, and watched a sky that might have blazed with light in ways we can barely imagine. Before we go any further, a small thing that will save confusion later. When we talk about the magnetic field weakening or the poles shifting, we are not talking about the geographic poles. The North Pole, the one at the top of every map, the one explorers race to reach, that's defined by Earth's rotation axis. It doesn't move in any meaningful way on human timescales. The magnetic poles are different. They're created by the churning liquid iron in Earth's outer core, and they wander all the time. Right now, the magnetic North Pole is drifting toward Siberia at a pace that has scientists paying close attention. The poles on your globe and the poles your compass points to are related but not the same thing. And 41,000 years ago, the difference between them became something stranger and more dramatic than at any point in recorded history. If you're listening to this right now and you're already starting to drift, that's exactly what this channel is for. These stories are built to carry you somewhere interesting on your way to sleep. Something real. Something that actually happened. Paced slow enough to let your mind wander alongside it. If you're finding them useful, follow on Spotify where the episodes are ad-free and music-free. Just the voice and the story. Nothing to jerk you back awake. There's a link in the description to support the work if you want to. And if you feel like leaving a comment before you go, tell me where you're listening from and what time it is there. I genuinely read them. It's one of the stranger and more wonderful parts of doing this, watching the map fill in. Someone in Tokyo at 2 in the morning, someone in Auckland just after midnight, someone in a Chicago apartment at 11 p.m. trying to quiet their brain down. If that's you, tell me. I'll see it. Now, 41,000 years ago. Most of what we know about deep prehistory comes from things that survived. Bones, tools, ash layers, pollen trapped in sediment, isotopes locked in ice. The magnetic field doesn't leave bones. It doesn't fossilize in any obvious way. So for a long time, scientists didn't know about the Laschamps Excursion at all. It was hiding in the rocks, waiting for someone to develop the right tools to find it. When they did find it, the implications were significant enough that researchers are still arguing about exactly what it meant for the world above the surface. What makes this story genuinely strange is the cascade of consequences that a weakened magnetic field could trigger. It's not just that your compass would spin. The field does something fundamental. It deflects charged particles from the sun, the constant stream of plasma and radiation called the solar wind, and it deflects higher energy particles from beyond our solar system, galactic cosmic rays. Strip that shield away and those particles reach the upper atmosphere in much greater numbers. That changes atmospheric chemistry. It affects ozone. It alters the rate at which certain isotopes are produced in the atmosphere. Isotopes that eventually fall into the ocean, into ice, into trees, leaving behind exactly the kind of fingerprints that scientists can read tens of thousands of years later. And so the story of the Laschamps Excursion is also a detective story. The crime scene is the planet itself. The evidence is buried in Antarctic ice cores drilled kilometers into ancient snow, in stalagmites growing in caves that haven't seen daylight in millennia, in the magnetic signatures baked into old lava flows when they cooled and locked the direction of the field in place like a photograph. Piece by piece, from sites scattered across the globe, researchers have been assembling a picture of a world without its magnetic armour, at least without most of it, for a period of time that may have been brief in geological terms, but was profound in its effects. We are going to follow that detective work tonight. We'll see how something invisible and ancient left traces we can actually measure. We'll think about what the sky might have looked like, what the radiation environment might have felt like at the surface, what a scrambled compass means for a migrating bird or a whale, or a band of early humans trying to navigate a new continent. We'll sit with the uncertainty too, because some of what scientists believe about this event is still contested, and the honest version of this story includes the parts we don't know yet. But we start with the field itself, because to understand what nearly vanished 41,000 years ago, you first have to understand what it is, and what it quietly does for every living thing on this planet, every single day, including right now while you're lying there, listening, the invisible shield holding steady above you. Deep inside the Earth, roughly 2,900 kilometers below the surface, there is a boundary where the solid rock of the mantle gives way to something entirely different. Liquid iron, an ocean of it, slowly churning, driven by heat escaping from the planet's core and set spinning by the rotation of the Earth itself. This is the geodynamo, and it is the reason your compass has ever pointed anywhere at all. The basic idea is surprisingly simple. Moving electrical charges generate magnetic fields. That's just physics. The same reason an electric current running through a wire creates a magnetic field around the wire. In Earth's outer core, the moving charges are the electrons in that churning liquid iron, and the field they generate is enormous. It reaches from the core all the way out through the crust, through the oceans, through the atmosphere, and thousands of kilometers into space. The geodynamo isn't one clean loop of current. It's a tangled, shifting collection of flows and eddies, which is why the field it produces is never perfectly symmetrical, never perfectly stable, always doing something slightly different from one century to the next. What that field creates around the Earth is called the magnetosphere. Think of it as an invisible bubble, though the shape is more complicated than that. On the side of Earth facing the Sun, the solar wind, that constant stream of charged particles and radiation pouring outward from the Sun, compresses the magnetosphere into something like a blunt nose. On the night side, it stretches out into a long trailing tail, like a comet's in reverse. The magnetic field lines deflect most of those incoming solar particles around the planet, the way a river splits around a stone. The particles don't vanish, they get redirected. Many of them flow around us and continue on their way. Others get funneled toward the poles, where the field lines converge and dip down toward the surface. That's where auroras come from, charged particles colliding with oxygen and nitrogen high in the atmosphere, producing those curtains of green and red light that people travel to Scandinavia and Alaska to see. So, in a normal, healthy state, the field is doing several things at once. It's deflecting solar wind. It's redirecting higher energy cosmic rays from beyond our solar system. It's protecting the upper atmosphere from the kind of sustained particle bombardment that, over millions of years, can actually strip a planet of its atmosphere entirely. Mars, which lost its global magnetic field billions of years ago, lost most of its atmosphere too. That's not a coincidence. Closer to everyday life, the field is doing quieter work. It's what compass needles respond to. It's what allows satellites in low Earth orbit to function without being overwhelmed by radiation. It's what migrating animals use to navigate. Birds, sea turtles, salmon, sharks, even certain bacteria carry biological compasses, magnetite crystals or similar structures that let them sense the field's direction and intensity. When you watch a humpback whale moving in a nearly perfect straight line across thousands of kilometers of open ocean, or a monarch butterfly returning to a specific forest in central Mexico it has never visited before, you are watching the magnetic field in action, woven into behavior, into biology, into the inherited knowledge of how to find your way home. A normal field has two qualities worth holding on to: direction and strength. Direction tells you where the magnetic poles are. Strength tells you how powerful the field is, how effectively it's doing all that deflecting and redirecting. Right now, Earth's field is at a strength that has maintained something like this for millions of years, with fluctuations but within a recognizable range. The poles wander, but they stay in roughly polar regions. The shield holds. What happens when the strength drops? When direction becomes unreliable, when the field loses its coherence and fractures into something patchy and confused, strong here, nearly absent there, the deflection weakens, more particles get through. The atmosphere absorbs more cosmic radiation. The chemistry of the upper atmosphere shifts. Animals following invisible lines through the ocean and sky suddenly find those lines scrambled or gone. That's not speculation. We know fields can weaken dramatically because it happened. 41,000 years ago it happened here, and the traces it left behind in rock, in ice, in the very atoms of ancient trees are what eventually told us so. To understand what happened 41,000 years ago, you have to know something slightly unsettling about Earth's magnetic field. It is not loyal, it looks loyal, if you only watch it for a human lifetime. North is north. Compasses behave themselves. Migrating birds arrive more or less where they should. But if you stretch your view out across millions of years, the story changes. The field is restless. It wanders. It weakens. Sometimes it flips. Geophysicists call the big flips geomagnetic reversals. In a full reversal, the global magnetic field reorganizes so completely that what we call the north magnetic pole ends up near the geographic south pole, and the south magnetic pole moves to the north. If you'd had a compass in your hand during one of these events, and you could somehow watch long enough, you would have seen its needle gradually stop pointing toward the Arctic and begin pointing toward Antarctica instead. Nothing about the planet's spin changes when this happens. The Earth does not tip over. The geographic poles, the points the planet actually spins around, stay exactly where they are. Day is still day, night is still night. The seasons still follow one another. What changes is the invisible field threaded through all of it. The north your compass cares about is magnetic north, not geographic north, and magnetic north can drift, split, fade, and reverse without the planet missing a single rotation. You can picture it this way. Imagine a spinning globe sitting on your desk. The little metal axle running through it marks the geographic poles. That's the rotation axis, stable on human timescales. Now imagine a bar magnet hidden inside the globe, not perfectly lined up, a little crooked, maybe even wobbling and shifting over time. That bar magnet is a rough stand-in for the geodynamo's output. The field it creates defines magnetic north and south. When geophysicists talk about pole movement, they're talking about the wandering ends of that invisible magnet, not the physical tilt of the whole Earth. A full reversal is the most dramatic version of that wandering. Over thousands of years, the field weakens, becomes disorganized, sprouts multiple poles, and then settles again with the opposite polarity. What used to be magnetic north becomes magnetic south. Volcanic rocks that cool during this time lock in the new direction like tiny compasses frozen in stone. When we collect those rocks today, measure their magnetization, and line up their ages, we see a long barcode of polarity, black for normal like today, white for reversed, alternating back and forth across deep time. That barcode is not evenly spaced. Sometimes Earth goes tens of millions of years without a reversal. The Cretaceous superchron, when dinosaurs still ruled the continents and birds were only just finding their wings, lasted nearly 40 million years with the field stuck in one orientation. At other times, the field seems to flip frequently, every few 100,000 years or less. On average, over the last few tens of millions of years, people often quote something like one reversal every couple 100,000 years. But that's like saying the average weather on Earth is mild. It hides the extremes. The timing is irregular, clustered, punctuated by long quiet stretches and bursts of activity. Whatever the core is doing, it does not keep a simple schedule. And even that barcode of clean black and white stripes leaves something out. Between the long, stable normal and reversed states, there are briefer, stranger episodes when the field seems to partly lose its grip, but then recovers without fully committing to a flip. These are called geomagnetic excursions. An excursion is like a failed reversal, or maybe a rehearsal for one. The field weakens dramatically. The magnetic poles wander far from their usual high-latitude haunts, sometimes into the tropics, sometimes looping and stuttering across the globe. In some reconstructions, the field even spends a bit of time in a reversed-like configuration before snapping back. But the key point is that it doesn't lock into a new long-term state. After a few thousand years at most, the system regains strength and returns to its original polarity. For creatures living through it, the difference between a full reversal and an excursion would not be about direction labels on a map. Most of them weren't using compasses. The difference would be about duration. A full reversal involves a protracted transition, and then hundreds of thousands to millions of years of the new configuration. An excursion is a momentary stumble, brief on geological timescales, but still long enough to matter for ecosystems and climates if the field's strength drops far enough. From our point of view, trying to reconstruct what happened long after the fact, excursions are trickier to see than full reversals. A full reversal leaves an unmistakable global signature. Volcanic rocks on every continent, seafloor crust spreading away from mid-ocean ridges, lake sediments building up year after year, all end up recording the shift from one polarity to the other. You can line up records from South America and Asia and the Atlantic and see the same flip, the same change in direction, at roughly the same time. It stands out. Excursions are more like whispers. The field may weaken, but not everywhere equally. Local anomalies can be strong. The poles wander, but perhaps not in the same pattern in every reconstruction. The total duration might be only a few hundred or a few thousand years. In the layers of sediment or lava flows, that's a thin slice, easy to miss or smear out. Dating those thin slices precisely is hard. Radiometric clocks may not resolve events on the order of a few centuries. Sedimentation can be uneven, eroded here, doubled there. Volcanic eruptions that might provide a clean timestamp don't always oblige by erupting at the right moment. So in many rock records, excursions show up ambiguously. A brief period of low field intensity inferred from how weakly magnetized the grains are, a strange looping direction that doesn't fit neatly into normal or reversed, an odd spike in cosmogenic isotopes hinting that more cosmic rays were getting through the atmosphere for a while. Put together, these clues suggest that the geodynamo shook itself, staggered, almost fell, but caught its balance and carried on. Despite those difficulties, a few excursions stand out clearly. Among them, one in particular has become the poster child, partly because it's relatively recent, partly because it left traces in many different kinds of archives. Around 41,000 years ago, during the time when Neanderthals still walked through Ice Age Europe and early modern humans were spreading across the old world, the magnetic field did something dramatic. It weakened to a fraction of its usual strength. The poles wandered far from their familiar positions, and for a short while, the field may have been globally organized in the opposite direction. This is what we call the Laschamps Excursion, named after a small village in central France, where its signature was first clearly recognized in cooled lava flows. It is not a full reversal in the classic sense. The field did not stay flipped. Within a few thousand years it had recovered its former polarity, but as an excursion it is one of the best studied we have. A rare case where multiple lines of evidence, magnetized rocks, deep-sea sediments, Greenland ice, even the annual growth rings of long-dead trees converge on the same story. Before we can use that story to ask whether Neanderthals noticed the sky changing, or whether climate systems shuddered in response, we have to understand how we first saw it at all. That takes us back to the lava fields near Laschamps, and to the scientists who realized that those ancient rocks were quietly pointing in the wrong direction. When geophysicists talk about magnetic records, they don't mean notebooks. They mean rocks. The story of Laschamps begins with one of the simplest, strangest facts about volcanic lava. As it cools, it remembers which way the magnetic field was pointing. The village of Laschamps sits on the flanks of an ancient volcanic landscape in the French Massif Central. Long before anyone lived there, eruptions spilled sheets of molten rock across the countryside. Those flows cooled and hardened into basalt, and then they just sat. Rain fell. Forests came and went. Glaciers advanced and retreated far to the north. People eventually built farms and roads, but deep inside those dark, solidified lava flows, tiny crystals were still quietly carrying a message from Earth's core. The message is written in something called remnant magnetization. To see how it forms, imagine standing near one of those eruptions while it's happening. Fresh lava roars out of a vent at more than 1,000 degrees Celsius. At those temperatures, the minerals inside it are too hot to hold a stable magnetic moment. Thermal agitation shakes everything around. Microscopic magnetic domains are jostled out of alignment, as if someone were constantly bumping the table. But as the lava spreads, slows, and begins to cool, something important happens. It passes down through a critical temperature range, different for different minerals, where the magnetic domains can suddenly feel the outside world. In that window, the ambient magnetic field becomes a kind of template. The tiny magnetic needles inside grains of iron-bearing minerals start to line up with the field direction, like a million microscopic compass needles agreeing on where north is. keep cooling and those domains freeze in place. Below that blocking temperature, thermal motion is no longer strong enough to randomize them. The rock goes from molten to rigid, and the orientation of those countless little needles is locked. From then on, unless the rock is heated back up past that blocking temperature or chemically altered, it carries a permanent imprint of the field's direction, and, more subtly, a clue to its strength at the moment it cooled. That imprint is remanent magnetization, a fossil compass preserved inside stone. Early paleomagnetists learned to exploit this. Take a chunk of basalt, measure the direction of its net magnetization in the lab, and you get a vector pointing toward where magnetic north was relative to that rock when it cooled. Measure many rocks of different ages, and you can begin to reconstruct how the field's polarity and intensity have changed through time. By the middle of the 20th century, this approach had already revealed the broad barcode of reversals, long periods where rocks recorded one polarity, then long periods of the opposite. It helped confirm seafloor spreading, plate tectonics, and the restless character of Earth's core. But not every rock fit neatly into that pattern. In the late 1960s and early 1970s, researchers working in the Massif Central started sampling the young volcanic flows near Laschamps. On a geological timescale, these rocks were almost brand new. Late Pleistocene, tens of thousands of years old at most. They expected them to record the same normal polarity as today's field, magnetic north roughly in the Arctic, south near Antarctica. They did not. When the samples were brought back to the lab, subjected to careful demagnetization to strip away any recent overprints, and then measured in magnetometers, the results were deeply odd. Instead of pointing roughly toward present-day north, many of the flows carried magnetizations that aimed almost the opposite way. The north recorded in those rocks was down near Antarctica. On paper, these French lavas seemed to be saying, "When I cooled, the field was reversed." That was a bold claim to hang on a handful of flows in one small region. At first, many researchers were cautious. Maybe some local quirk was confusing the picture. Volcanic rocks can acquire additional magnetizations later in their life if they get reheated, struck by lightning, or chemically altered. Faulting and tilting can physically rotate layers after they form. If you don't correct for those effects, you can trick yourself into thinking the field was doing something dramatic, when really the rock just had a complicated history. So the early Laschamps data lived in an uncomfortable space, intriguing but not yet decisive. A possible short-lived reversal or a geological red herring. The way out of that ambiguity was repetition. Teams went back to the field and sampled more flows. They drilled cylindrical cores from different parts of the same lava units, from neighbouring units above and below, from dikes cutting through older rocks. They mapped out the local geology in detail to understand which layers were genuinely in place and which had been disturbed. In the lab, they applied stepwise demagnetization, heating or exposing samples to alternating magnetic fields in small increments to peel away any secondary magnetizations and reveal the stable original component. The more they looked, the stranger and more consistent the pattern became. A whole sequence of flows in the Laschamps area shared the same reversed-like direction. Not just one odd layer, but a stack of them, sandwiched between older and younger rocks that carried the expected normal polarity. The transition from normal to reversed, like directions and back again, was abrupt in geological terms, confined to a relatively thin slice of the volcanic record. If this were just a local quirk, a lightning strike, a small intrusive body reheating things, you'd expect the effect to be patchy, inconsistent, sensitive to position. Instead, different flows, sampled in different places by different teams, kept telling substantially the same story. Something had happened to the global field while those lavas were cooling. Still, volcanoes in France are only one viewpoint. The next question was obvious. Did anything similar show up elsewhere? Soon hints began to appear from far beyond the massive central. Marine cores drilled from the Atlantic and Pacific seafloors showed brief intervals where the magnetic grains in deep-sea sediments recorded anomalous directions and very low field intensities. A few other young volcanic sequences from places like Hawaii and the Canary Islands carried magnetizations that didn't point where they should for a normal field. When researchers lined up the age estimates, the anomalies clustered near the same window of time. It wasn't a perfect fit at first. Dating methods for such young rocks and sediments came with sizable uncertainties. Radiocarbon calibration curves were still being refined. Potassium-argon and argon-argon dating on basalts were improving, but pinning down an event that might have lasted only a couple of thousand years was pushing those techniques close to their limits. So in the early decades, Laschamps sat in the literature, under different names and with somewhat fuzzy boundaries: a short reversal, a momentary flip, a geomagnetic excursion near the end of the last glacial cycle. Different groups gave slightly different ages. Some records seem to show a clean reversal-like direction, others a more complex looping path. The overall impression was of the geodynamo doing something unusual, but the exact choreography was still blurry. What changed over the following decades was not just the accumulation of more data, but the sharpening of the clocks. Radiocarbon dating of organic material in sediments and speleothems became better tied to absolute timescales. Argon-argon dating on volcanic rocks was refined, squeezing down uncertainties. Tephrochronology, the use of chemically fingerprinted volcanic ash layers as time markers, helped link distant records together. As these methods improved, the apparently scattered hints of a magnetic disturbance around 41,000 years ago began to snap into focus. The reversed-like directions in the Laschamps lavas lined up with intensity minima and directional swings in marine sediments. Those, in turn, lined up with spikes in cosmogenic isotopes in ice cores and tree rings, which we'll come back to. What had once looked like a curious French anomaly now appeared as part of a global event, visible from the middle of the Atlantic to the high latitudes of Greenland. With that convergence, scientific interpretation evolved. The cautious talk of a possible local reversal gave way to a more confident classification. This was an excursion, now named for the place where its volcanic record was first clearly recognized. Not a full, long-lasting reversal of the entire barcode, but a dramatic, relatively brief departure from normal behavior that left marks in many independent archives. The lavas at Laschamps had been right all along. They were simply the first to speak loudly enough for us to notice. Only after that realization did it become possible to ask finer questions. How weak did the field become? How long did the disturbed state last? Did the field truly flip into a reversed configuration worldwide? Or did it only flirt with that state while intensity collapsed? To answer those, rocks are not enough. You need other clocks, other witnesses, sediments settling grain by grain, ice building up layer by layer, trees growing ring by ring under a slightly harsher sky. You need to learn how to date a magnetic near collapse. If you want to know what happened during a magnetic near collapse, you don't just need evidence that it happened. You need a clock. More than one, actually. The Laschamps lavas told us the field had swung into strange territory. But a lava flow on its own can't tell you whether that disturbance lasted 500 years or 5,000. It can't tell you whether the weakest phase lined up with a particular climate oscillation, or with changes in solar activity, or with anything else. For that you need to know when, in absolute time, those rocks froze in their magnetization. And that's where the hard work begins, turning physical samples into dates. Start with the most direct clock for volcanic rocks, radioactive isotopes. Hot magma doesn't just contain iron-bearing minerals that record magnetization. It also contains trace elements like potassium, argon, uranium, thorium. Some of these elements are unstable, constantly transforming themselves at known rates. When a lava erupts and cools, it effectively resets certain radiometric clocks. Argon, for example, is a noble gas. In molten rock, it tends to escape. When the lava solidifies, new argon produced by the decay of radioactive potassium is trapped inside the mineral lattice. From that moment forward, the ratio of potassium-40 to argon-40 begins to change in a predictable way. Measure that ratio in the lab, and in principle, you can calculate how long it's been since the rock cooled through the blocking temperature. That's the basis of potassium-argon and argon-argon dating. For the Laschamps flows and other young basalts, geochronologists use refined versions of these methods. They crush and irradiate mineral separates, carefully quantify isotopic ratios, correct for atmospheric argon, and run repeated analyses to catch outliers. Each result comes with an uncertainty, plus or minus a few thousand years for older rocks, sometimes 1,000 years or less for younger ones if you're lucky. On its own, a single argon-argon date might say something like, this flow is 42,000 years old, give or take 2,000. That's useful but not razor-sharp, and the Laschamps Excursion is thought to have unfolded over only a couple of thousand years. So geologists reached for other clocks. Sometimes lavas erupt onto landscapes that already contain datable materials. Soils, peat layers, lake sediments, even the charcoal from ancient fires. Those materials contain carbon, and a small fraction of that carbon is radioactive carbon-14, constantly produced in the atmosphere by cosmic rays and then taken up by plants, animals, and indirectly everything that breathes or eats. When an organism dies, it stops exchanging carbon with the atmosphere. The carbon-14 inside it begins to decay at a known rate. Measure the remaining carbon-14 in a bone, a bit of wood, or a fragment of organic rich sediment, and you can estimate how long it's been since that material was part of something living. Radiocarbon dating, though, comes with its own complications, especially around 40,000 years ago. The production of carbon-14 in the atmosphere is not constant through time. It wobbles with changes in the magnetic field and solar activity. To turn radiocarbon years into calendar years, you need calibration curves built from independently dated archives, tree rings, corals, speleothems. Those calibration curves have improved dramatically over the last few decades. Early versions introduced extra uncertainty. Later versions, informed by long tree ring sequences and uranium-thorium, dated corals, smoothed out many of the bumps. Still, each calibration adds another layer of error bars. The final age might be 41,200 calendar years, plus or minus several hundred. So you can see the problem. One lava tells you the field's direction. An argon-argon date puts it near 42,000 years ago. A soil buried beneath that lava yields a radiocarbon age that calibrates to around 41,000. A nearby stalagmite growing in a cave holds a subtle shift in its trace elements that might be tied to the same eruption, and uranium-thorium dating pins that changed to 40,800 years ago. Each clock ticks with slightly different noise. None is perfectly precise. This is why stratigraphy, the study of layers, matters so much. If you can't make one perfect clock, you build a system of overlapping clocks, each constraining the others. Imagine a hillside in the Massif Central. At the bottom, an older basalt flow with normal polarity. Above it, a soil horizon. Above that, the Laschamps flow with its reversed like direction. Higher still, another soil, then a younger flow with normal polarity again. Even if each radiometric date on its own is fuzzy, the layering tells you the order of events. The lower normal polarity flow must predate the excursion. The upper normal polarity flow must postdate it. The soils bracket the timing of lava emplacement and preserve any organic material that can be radiocarbon dated. If a distant lake core contains a layer of volcanic ash that can be chemically matched tephrochronology to one of those flows, the entire sequence can be tied into a broader regional stratigraphy. Multiply that logic across many sites: France, the Canaries, Hawaii, Iceland, the seafloor. Each place adds another local stack of events, another set of radiometric dates, another chance to align things using ash layers, paleoclimate markers, and eventually cosmogenic isotope peaks in ice cores. The power here is not any single measurement. It's the convergence of multiple independent clocks, each based on different physics, different materials, different assumptions. When potassium-argon ages, uranium-thorium dates, calibrated radiocarbon, and layer counting in ice cores all point to a disturbance centered near 41,000 years ago. The probability that you are looking at a real global event grows very high. That doesn't mean the timing is perfectly nailed down. Researchers talk in terms of error bars and confidence intervals, statistical ways of expressing how tightly they think they've constrained an age. For the Laschamps Excursion, early estimates placed it somewhere between about 30,000 and 50,000 years ago, with different datasets favouring different ranges. As methods improved, that window narrowed. High-resolution marine cores dated with multiple techniques suggested the heart of the disturbance lay around 41,000 years ago. Ice cores with annual or near-annual resolution added finer detail. Radiocarbon calibration curves extended back beyond 40,000 years allowed tree ring sequences and cave deposits to speak the same chronological language. By the early 21st century, many studies converged on a picture where the main Laschamps intensity minimum and directional instability occurred roughly between 42,000 and 40,000 years ago, with the weakest phase, what some papers call the core of the excursion, lasting on the order of several hundred to a millennium or two. But phrase choices stay cautious: about, around, on the order of, likely between. Different records still disagree on the exact onset and recovery times by a few hundred years. Some show hints of precursor wobbles or regional complexity that may or may not be real. Sample quality varies. Not every lava is pristine, not every sediment core is undisturbed, not every ice layer is easy to count. There are also fundamental limitations in the clocks themselves. Radiocarbon becomes very sparse and tricky to measure as you approach its effective limit, around 50,000 years. Argon-argon dating struggles with very small age differences on very young rocks. Uranium-thorium works best in certain minerals and environments. Even ice core layer counting can be ambiguous when dust and volcanic markers blur together. So when you read a number like 41,000 years ago for the Laschamps near collapse, it's worth remembering what that really means. It's not a single sharp tick on a cosmic stopwatch. It's a best estimate emerging from hundreds of overlapping measurements, each with its own uncertainties, all pressed together until a coherent window of time takes shape. What is well constrained is the general position of the event in the last glacial cycle. Late Pleistocene, just before the major expansion of ice sheets leading toward the last glacial maximum. Multiple independent archives agree that the field intensity plunged to a fraction of its usual strength, and that directional behavior was highly unstable, somewhere in the neighborhood of 42 to 40,000 years ago. What remains debated are the finer details. Exactly how fast did the field weaken and then recover? Did the field fully reverse, even for a short time? Or did it just wander into a reverse-like state without locking in a true global flip? Were there short-lived rebounds or regional asymmetries hidden inside that broader minimum? Different datasets, with different resolutions and noise, give slightly different answers. To peel back those layers, scientists turned to some of the most delicate clocks of all, annual rings in ancient trees, and the slowly accumulating snow of polar ice. These archives carry not just time, but a record of the cosmic rain that bathed Earth when its magnetic shield sagged. In those, the timing of a magnetic near collapse is written not in lava and argon, but in atoms born from starlight. When a cosmic ray slams into Earth's atmosphere, it doesn't leave a neat, obvious scar. It doesn't carve a crater or paint a glowing streak you can see from the ground. It arrives at nearly the speed of light, hits a molecule of nitrogen or oxygen, and shatters into a cascading spray of secondary particles. Most of those vanish in fractions of a second. But a few of the fragments do something subtle and important. They transform other atoms. Some of the secondary neutrons born in that atmospheric shrapnel collide with ordinary nuclei and knock them into new configurations. You start with nitrogen-14, say, and after a collision and an escape of a proton, you end up with carbon-14. Or you start with oxygen and end up with beryllium-10. These are cosmogenic isotopes, elements whose very existence on Earth in their radioactive form is a kind of ledger entry for cosmic ray activity. Carbon-14 is the famous one, the backbone of radiocarbon dating. Beryllium-10 is less well known outside geophysics, but for magnetic field history, it's just as important. Both are created in the upper atmosphere when high-energy particles from space smash into air molecules. Both are produced in greater or lesser amounts, depending on how many cosmic rays actually make it that far down. And that, in turn, depends on two shields, the Sun's magnetic wind and Earth's own magnetic field. Picture Earth wrapped in its geomagnetic cocoon. When the field is strong, it bends and deflects a large fraction of incoming charged particles. Only the most energetic cosmic rays, or those arriving near the polar caps where field lines are open, manage to reach the atmosphere in large numbers. When the field is weak, that shield thins, more particles penetrate, more atmospheric nuclei get shattered, more carbon-14 and beryllium-10 get made. The basic logic is simple. Weaker magnetic shielding means more cosmic rays mean more cosmogenic isotopes in the air. If you can find long, continuous archives that sample the atmosphere over tens of thousands of years, and if you can measure tiny variations in these isotopes through those archives, you can reconstruct a history of cosmic ray influx. In practice, that if hides a lot of complexity. Start with beryllium-10. Once it's born in the upper atmosphere, beryllium-10 sticks to aerosols and dust particles. It doesn't stay suspended forever. It gets rained out or snowed out, washed from the sky, and eventually trapped in whatever surface reservoir is accumulating at that time over polar regions that reservoir is snow. Year after year, winter after winter, fresh snowfall blankets Greenland and Antarctica. Each layer contains trace amounts of beryllium-10 produced in the air above. Over time, those layers get buried and compressed. Snow becomes firn, then ice. Air bubbles get sealed. The stack gets thicker. If that ice remains undisturbed, it forms an archive, a chronological column where depth corresponds more or less to age. Drill a core down through that ice, bring it to the lab, and you can slice it into samples representing decades, years, even individual seasons. Melt those samples and count the atoms. The concentration of beryllium-10 in each slice reflects, among other things, how many cosmic rays were hitting the atmosphere when that snow fell. Long Greenland and Antarctic ice cores Grip, GISP-2, NDRIP, Epica, Dome C, Dome Fuji have now yielded continuous beryllium-10 records stretching back hundreds of thousands of years. These records are noisy, full of wiggles and spikes. Some variations track solar cycles, some track changes in atmospheric circulation and precipitation, but lying underneath the weather and the sun's moods is a slower, broader modulation from Earth's magnetic field. Around the time of the Laschamps Excursion, those records show something striking, a broad hump, a sustained increase in beryllium-10 production lasting on the order of a couple of thousand years, with a pronounced peak near the centre. In some cores, that peak reaches values roughly double the long-term background, interpreted as a change in global production. That kind of amplification suggests a significant weakening of the geomagnetic shield. More cosmic rays got through, more beryllium-10 was synthesized, more of it ended up frozen into the ice that was falling as snow somewhere over the polar plateau 41,000 years ago. Carbon-14 tells a parallel story, but through a different medium. Newly minted carbon-14 in the upper atmosphere quickly oxidizes, joining the enormous reservoir of carbon dioxide. From there, it cycles through the atmosphere, oceans and biosphere. Plants take up that CO2 during photosynthesis. Animals eat the plants. Everything living ends up with a small, steady fraction of its carbon atoms in the radioactive form. When the production rate of carbon-14 changes, the entire carbon cycle gradually adjusts. Over a few decades to a few centuries, the ratio of carbon-14 to stable carbon in the atmosphere shifts. That shift propagates into tree rings, peat, shells, bones, and dissolved inorganic carbon in the ocean. The trick is to find archives where you can read that ratio with high time resolution and good independent dating. Ancient trees, especially long-lived conifers and preserved subfossil logs, are among the best. Each year, a tree adds a ring of new wood. That ring locks in the carbon isotope ratios of the atmosphere at the time it grew. If you can sequence those rings and cross-match patterns of thickness and isotopic fluctuations between many overlapping trees, you can build a continuous year-by-year timeline. Dendrochronologists have done exactly that for large portions of the Holocene. For older periods, including around 41,000 years ago, the ring sequences become patchier and more uncertain. But there are still valuable fragments, preserved kauri trees from New Zealand bogs, for instance, and other ancient timbers that bridge key intervals. Measure carbon-14 in those rings, and you get a direct record of atmospheric radiocarbon concentration through time, modulated, of course, by the carbon cycle's internal lags and mixing, but still sensitive to production changes. Because radiocarbon dating itself depends on knowing the baseline carbon-14 level through time, any mismatch between radiocarbon ages and independently dated materials shows up as a wiggle or step in the calibration curves. When production spikes, living things incorporate more carbon-14. Samples from that interval will appear too young if you assume a constant production rate. To correct for that, calibration curves like INTCAL for the northern hemisphere and SHCAL for the southern build in those production anomalies explicitly. Around the Laschamps Excursion, radiocarbon calibration curves show a prominent feature, a region where apparent radiocarbon ages deviate strongly from calendar ages inferred from other methods. Interpreted as a production change, that feature implies a marked increase in carbon-14 generation, aligning in time, within error with the beryllium-10 hump in ice cores. Put simply, both the polar ice and the ancient trees are telling you, around 41,000 years ago, the cosmic radiation environment at Earth's surface intensified. More cosmogenic isotopes were being made. It's tempting to draw a straight, simple line from that fact to the geomagnetic field. Field weakens, cosmic rays surge, isotopes spike, and indeed much of the signal likely reflects exactly that. A sagging magnetic dipole allows more particles into the atmosphere, especially at lower latitudes, boosting global production of beryllium-10 and carbon-14. But the real system is less tidy. Solar activity, for instance, can modulate cosmic ray flux on timescales of years to millennia. When the Sun is magnetically active, solar maximum, its strengthened solar wind shields Earth more effectively from galactic cosmic rays, reducing cosmogenic isotope production. When the Sun is quiet, solar minimum. More cosmic rays leak through and production rises. Atmospheric circulation and precipitation patterns also matter, particularly for beryllium-10, a change in storm tracks over Antarctica or Greenland. can alter where and how efficiently beryllium-bearing aerosols are scavenged from the air, changing their concentration in snowfall without any shift in global production. Volcanic eruptions, by injecting aerosols into the stratosphere, can temporarily enhance beryllium-10 deposition in certain regions. Even changes in the carbon cycle, how quickly the ocean takes up CO2, how much carbon is stored in soils and vegetation, can affect how a production pulse of carbon-14 is expressed in tree rings or marine carbonates. In other words, cosmogenic isotopes are not pure magnetometers. They are integrators of multiple influences: geomagnetic field strength, solar modulation, atmospheric transport, precipitation, carbon cycling. Teasing out the specific contribution from Earth's field requires comparing many records, building models, and looking for patterns that are globally coherent rather than regional or short-lived. During the Laschamps interval, that comparison has been done repeatedly. The broad, multi-century to millennial scale increase in beryllium-10 appears in both Greenland and Antarctic cores. The carbon-14 anomalies show up in calibration curves built from different archives and dating methods. The timing lines up within reasonable uncertainties with independent geomagnetic intensity reconstructions from marine sediments and lavas. Individually, each dataset is messy, with its own noise and local quirks. Together, they converge on a consistent picture. While Earth's magnetic field stumbled through its excursion, the planet was bathed in a stronger flux of cosmic radiation than usual. That enhanced radiation left its spectral signature not just in volcanic rocks and seafloor sediments, but in the chemistry of ancient ice and the atomic composition of long-dead wood. Those are the cosmic fingerprints, invisible particles from distant stars, written into the slow growth of glaciers and the quiet widening of tree trunks, waiting tens of thousands of years for someone to learn how to read them. Once you accept that those isotopic spikes mark a real increase in cosmic ray access to our atmosphere, a more concrete question follows: how weak did the magnetic field actually get? And for how long did our planet stand with its shield so thin? To answer that, we have to translate those cosmic fingerprints into something more familiar: magnetic field strength. Geophysicists usually talk about the strength of Earth's dipole, the big planet-scale bar magnet component of the field. Today, that dipole gives us an average surface intensity of about 50 microteslers at mid-latitudes. The exact number doesn't really matter for our purposes. What matters is the ratio, how the field at Laschamps compared to that modern reference. When you combine the evidence from lava flows, marine sediments, and cosmogenic isotopes, a broad picture emerges. During the deepest part of the Laschamps excursion, the dipole seems to have collapsed to somewhere between about 5 and 10% of its current strength. Some reconstructions put the minimum even lower for brief intervals, flirting with just a few percent. Others are a little more conservative. But the general consensus is that the main global dipole was reduced by at least a factor of 5, and probably closer to an order of magnitude, compared to the modern field. That's an extraordinary drop. If you could stand there with a magnetometer in your hand 41,000 years ago, under that anemic field, the needle would still react. The field didn't go to absolute zero, but it would have been more like the magnetic environment you find today a few planetary radii out in space, in the fringes of the magnetosphere, than what we experience on the surface now. The descent to that minimum wasn't instantaneous. Long before the moment we call Laschamps proper, the field had been weakening. Intensity reconstructions from marine sediments suggest that the dipole started its serious slide a few thousand years earlier. If you ran time in fast forward, you'd see the field's strength wobbling and trending downward, like a spinning top losing speed. For several millennia leading up to the excursion, the dipole moment gradually diminished, perhaps to half, then a third, then a quarter of its present value. Directional records, tiny compass readings locked into sediments and lavas, begin to show more scatter. The virtual geomagnetic poles inferred from those directions start wandering farther from geographic north, tracing loops that look less like the tight circles of a healthy field and more like drunken scribbles. Then comes the truly unstable phase. Around 41,000 years ago, give or take a few centuries, the field directions in many records swing dramatically. In some lavas from central France, the magnetic directions jump toward what would be south in today's configuration. In marine cores, the recorded field at the seafloor points towards strange, transient pole positions far from either geographic pole. This is the heart of the excursion. Low dipole strength, wild directional behavior. It doesn't last long in geological terms. The most extreme part of the chaos, the period when directions are most unstable and the dipole is at its absolute minimum, might have persisted for only a few centuries, perhaps up to a millennium. Wrapped around that are broader shoulders of disorder, a couple of thousand years during which the field is distinctly weaker and more capricious than usual, but not quite at its most deranged. After that, the system begins to claw its way back. Field intensity starts to recover. Sedimentary records show a gradual rise in relative paleointensity. The virtual poles, instead of darting around the globe, begin to cluster again toward high latitudes. Within perhaps 1,000 to 2,000 years after the deepest part of the excursion, the geomagnetic field looks, from the perspective of a paleomagnetist, normal again, strong, dominantly dipolar, with a north and south pole roughly where we expect them. So in broad strokes, you can divide the event into phases. First, a protracted weakening phase, millennia of declining dipole strength, still with a recognizably north-south structure, but growing more feeble. Then an unstable phase, centuries to 1,000 years of highly reduced dipole intensity and rapidly changing directions, with virtual poles wandering far from their usual haunts. Then a recovery phase, field strength marching back upward, directions settling, the global dipole reasserting itself. At no point did Earth entirely lose its magnetic field. What it lost was the clean, simple, two-pole structure that makes navigation easy and shielding efficient. Deep inside the planet, the geodynamo never stopped. Liquid iron and nickel in the outer core continue to convect and swirl. But the pattern of that flow changed in ways that disrupted the global dipole and allowed other components of the field, the smaller scale, higher order structures, to dominate for a time. This is where the idea of multiple poles comes in. We're used to thinking of Earth as having one north and one south magnetic pole, neatly opposite each other. That's a useful approximation when the dipole component is strong. But the full magnetic field of the planet is more complex, full of bumps and wiggles, like a weather map of highs and lows. Normally the dipole term dwarfs the rest. It smooths over the complexity. When the dipole weakens dramatically, those other harmonics matter more. Regions of locally strong field can appear at odd latitudes. What we casually call the pole can split into several high-intensity patches. The overall shield becomes patchy and asymmetric. Numerical simulations of the geodynamo supercomputer experiments that solve the equations of fluid motion and electromagnetism in a rotating convecting sphere routinely produce this kind of behavior when they're pushed into reversal or excursion-like states. The dipole collapses. The field's energy redistributes into non-dipolar modes. Multiple magnetic poles pop up at the surface, wander, merge, and fade. Eventually, the dipole re-emerges, sometimes flipped, sometimes in its original orientation. For the Laschamps event, the geological data aren't detailed enough to draw a full vector map of the field as it twisted through those instabilities. But several independent lines of evidence point to strong geographic variation. Cosmogenic isotope production is one clue. If the shield had become uniformly weak everywhere, you'd expect a very consistent enhancement in production at all latitudes. Instead, Beryllium-10 records suggest that the increase was particularly dramatic at lower and mid-latitudes, the very regions normally best protected by a strong dipole. That implies that the cut-off rigidity for cosmic rays, the effective barrier energy set by the field, dropped more there than near the traditional polar caps. Paleomagnetic records from widely separated sites tell a similar story. Some regions show extremely low local field intensities and bizarre, looping virtual pole paths during the excursion. Others, while clearly affected, retain somewhat stronger local fields and less extreme directional swings. In other words, the magnetic umbrella did not thin evenly. It frayed in places, tore open in others, and left a few patches relatively intact. A person living in what is now, say, Central Europe or North Africa at the height of Laschamps might have experienced a very different radiation environment than someone in southern South America or near the equator in the Pacific. The field geometry determined where charged particles could funnel in most easily. Some regions would have had something closer to today's polar exposure, others something worse. How precisely can we reconstruct those patterns? That's where current models meet their limits. We can estimate the global dipole moment fairly well, within factors of 2 or so by combining relative paleointensity data from many sites and anchoring them to a few absolute measurements from well-dated lavas. We can trace broad directional changes and identify intervals of instability. We can use cosmogenic isotopes to constrain how permeable the shield must have been, on average, to cosmic rays. But we can't yet resolve the fine-scale structure of the field everywhere on Earth at yearly or even century-level resolution 41,000 years ago. The data are too sparse in space and time. Lavas record snapshots separated by thousands of years. Sediments average over decades to centuries. Ice cores and tree rings tell us about the integrated cosmic ray flux, not the detailed geometry of the magnetosphere. So, models of the Laschamps field are, by necessity, smoothed reconstructions, guided by a few scattered anchoring points, and by dynamo simulations that may or may not capture all the relevant physics. They tell us that the dipole plunged to a fraction of its usual strength, that the field's direction wandered wildly for a brief geological instant, that the geometry likely fragmented into multiple poles and patches, and that the shielding Earth offers against charged particles became weaker and more uneven. They do not yet tell us exactly what the sky looked like at each latitude, which valleys had the worst radiation, or how quickly, year by year, the compass would have drifted. For that level of detail, we're still in the dark. But even the broad outline is enough to imagine a very different world. A planet where the invisible magnetic skeleton was temporarily disordered, where the boundaries of safe and unsafe sky shifted, and where the usual rules about north, south, and shelter from the cosmos no longer quite applied. Under such a weakened, tangled field, what would the surface of Earth have felt like? How would the sky have changed, night after night, for the humans and animals living through that strange interval? To answer that, we have to look up. Under a strong, well-behaved magnetic field like today's, most of the drama happens far away from where most people live. The solar wind streams past Earth, the magnetosphere deflects it, and the places where charged particles slip through, follow magnetic field lines, and crash into the upper atmosphere are mostly confined near the poles. That's why our brightest auroras today hug high latitudes: Alaska, Scandinavia, Antarctica. The glow is the visible signature of particles spiraling down funnels in the magnetic field and colliding with atoms tens or hundreds of kilometers above the surface. When the dipole collapses, those funnels don't behave the same way. With the field weakened to a small fraction of its normal strength, and with multiple poles and strange patches scattered around the globe, the regions where charged particles can access the atmosphere expand and shift. The auroral oval doesn't stay neatly wrapped around the Arctic and Antarctic. It stretches, warps, and in some models slides toward lower latitudes. So imagine standing somewhere that today we'd call temperate. Central Europe, northern China, the Mediterranean. Places where, in our time, auroras are rare, a once-in-a-lifetime treat during exceptional storms. Under Laschamps conditions, those skies may have looked different. Not necessarily every night, not all the time. Aurora depends on the sun too. It brightens during solar storms and fades during quiet periods. The 11-year solar cycle would still have been ticking away 41,000 years ago. But with the shield so compromised, and with magnetic funnels opening into lower latitudes, ordinary solar activity could have produced auroral displays far closer to the equator than we're used to. Instead of delicate curtains confined to polar twilight, sheets of diffuse glow might have appeared overhead in what is now France, or northern Africa, or Patagonia. Soft greens and reds breathing across the stars more frequently, more broadly. Maybe often enough that for some human groups the lights in the sky weren't a rare omen, but a recurring part of the nocturnal landscape. We can't map this precisely. There's no camera trap for ancient auroras. But when we combine the low dipole strength with evidence of enhanced cosmic ray access at mid-latitudes, the simplest inference is that the border between auroral zone and safe zone blurred and wandered. More of the planet sat under a sky that, at least during active solar intervals, could ripple and glow. Auroras are just the visible tip of the story. The more fundamental change is invisible: ionization. When high-energy particles from space hit the upper atmosphere, they knock electrons off atoms and molecules. This creates ions and free electrons, alters the chemistry of the air, and changes its electrical properties. Under a robust field, most of this activity is concentrated near the poles, with a background drizzle everywhere else. Under a feeble, patchy shield, the drizzle turns to a steadier rain, and it falls over a wider area. Cosmogenic isotope records tell us that, during Laschamps, the flux of energetic cosmic rays reaching the lower atmosphere roughly doubled, maybe more, depending on latitude. That's a global average. Locally, in regions where the field was especially weak or oddly configured, the increase could have been higher. More particles means more ion pairs created per second in the air column above you. In practical terms, this would have thickened the ionosphere, especially during the day and at middle latitudes. Radio engineers today worry about how geomagnetic storms and solar flares disturb the ionosphere because it changes how radio waves propagate. 41,000 years ago, there were no radios, but the physics was the same. The sky itself would have been a more electrically active medium. That heightened ionization feeds into chemistry. Energetic particle showers split molecular nitrogen and oxygen, generating odd nitrogen and odd hydrogen species that participate in catalytic cycles. Some of these cycles destroy ozone in the stratosphere. Others produce different reactive compounds. Later we'll talk about what that might have meant for climate. For now, it's enough to say that during the Laschamps Excursion, the atmosphere was being chemically stirred from above more vigorously than usual. What about radiation at the surface? Did the ground itself become dangerous? Here it helps to separate what we mean by radiation. There's ultraviolet light from the sun, largely filtered by ozone. There's the cascade of secondary particles produced when high-energy cosmic rays slam into the atmosphere: muons, neutrons, electrons and gamma rays. And there's charged particle precipitation along magnetic field lines, mostly affecting the upper atmosphere, and, to a lesser extent, high altitudes. A weaker geomagnetic field doesn't make the sun suddenly brighter. What it changes is how many cosmic rays and solar energetic particles can penetrate to low altitudes, and where the primary cosmic rays still do most of their damage high in the column. By the time their showers reach the ground, what matters are the secondary particles, especially muons, which can punch through hundreds of meters of rock and water. Models that couple paleomagnetic reconstructions with cosmic ray physics suggest that, globally, ground-level radiation dose from cosmic ray secondaries may have increased by something like a factor of 2 to 3 during the weakest phase of Laschamps. At high latitudes and high altitudes, mountain environments, upland plateaus, the enhancement could have been somewhat larger. Near sea level at low latitude, probably smaller. Those are not extinction-level doses. They're not the kind of spike you'd get if a nearby supernova went off, or a gamma-ray burst hit us directly. But they're not trivial either. Over generations, a persistent, planet-wide uptick in background radiation subtly raises mutation rates. For individuals, it slightly increases the risk of things like cancer, though disentangling such long-term, low-level effects in ancient populations is essentially impossible. Who would have been most exposed? High-latitude populations, because the shielding is weakest there. High-altitude populations, because there's less atmosphere above them to absorb particle cascades. People who spent a lot of time in open, unsheltered landscapes under a thin, cold sky would have taken more dose than groups living in lowland forests, deep valleys or caves. Caves, in particular, are excellent shields. Even a few meters of rock dramatically cut the flux of secondary particles. Later, when we talk about human and Neanderthal use of caves, keep that in mind. Shelter from wind, rain, and predators is obvious. Shelter from a noisier cosmos is less obvious, but real. There is another possible surface effect of all this ionization, one that has attracted interest but remains speculative: lightning. The exact physics that triggers a lightning strike is still not fully solved. One line of thinking suggests that cosmic ray showers can help seed the initial breakdown of air in thunderclouds, providing conductive paths that collapsing electric fields can then exploit. If that's true, and the evidence is suggestive but not conclusive, then an increase in cosmic ray flux during a geomagnetic excursion might lead to more frequent lightning, or at least alter its distribution. Under Laschamps, with a weakened field and more particles penetrating the atmosphere, electrical storms might have been more active in some regions. Perhaps flashes more common over certain mountain ranges or mid-latitude continents, where both storm formation and particle access aligned. Or perhaps the effect was minor, drowned out by the complexities of weather and climate. We don't have a lightning fossil record to compare. Charcoal in lake sediments, fire scars in trees, and soot in ice cores can tell us about fire activity, but disentangling human-made fires, climate-driven fires, and lightning-initiated fires, then tying those back to cosmic ray flux, is a chain with many shaky links. So increased lightning during Laschamps remains a plausible idea, not a demonstrated fact. All of these changes share a theme. The planet didn't suddenly become uninhabitable. The sun rose and set. Seasons came and went. But the quiet background conditions that we take for granted, the invisible cocoon of magnetic protection, the normal rate at which the upper atmosphere is ionized by space weather, the usual patterns of aurora and lightning shifted. For the creatures living under that sky, the difference would have been experiential, not abstract. More nights with faint glows sliding along the horizon or spilling overhead. A slightly harsher invisible rain of particles, especially in polar and high-altitude regions. Perhaps a world where storms cracked more often with lightning, or in slightly different places, though we can't be sure. And moving beneath that restless sky were humans and other animals already engaged in their own struggles for survival. To understand how this altered radiation environment might have touched them, we need to fold the physics back into the living world, into ozone, climate, and the thin layer of air and water where life actually resides. When you start talking about ionization and particle rain, the next question almost asks itself: what happens to the actual air we breathe? High-energy particles don't just make pretty lights and extra electrical noise. When they slam into the upper atmosphere, they kick off chemical reactions, especially in the thin, cold layers where ozone lives. Ozone is that fragile sunscreen wrapped around the planet, most of it sitting between about 15 and 35 kilometers up, quietly absorbing the sun's harshest ultraviolet. Change the chemistry up there, and you can, in principle, change how much UV reaches the surface and even nudge the climate. The basic idea is straightforward, even if the details get messy. When cosmic rays or solar energetic particles hit the atmosphere, they split nitrogen and oxygen molecules. Those fragments recombine into reactive species, odd nitrogen compounds like NO and NO2, and odd hydrogen compounds like HO and HO2. These little radicals don't stick around politely. They participate in catalytic cycles. A radical meets ozone, reacts, regenerates itself, and can go on to destroy many ozone molecules before finally being taken out of circulation. Under a quiet sky, there's a balance. Ozone is constantly being created and destroyed. Under a louder sky with more particles drumming through, that balance can tip. Climate modelers have tried to ask a simple question about Laschamps. If you turn down the magnetic field, crank up the particle flux, and let the atmospheric chemistry run, how much ozone do you lose? The answers are not simple at all. Some simulations, especially the early ones, painted a dramatic picture. Assume a very weak field, assume a fairly active sun, and feed the chemistry with a generous dose of high-energy particles. In those scenarios, global average ozone could drop by something like 10 to 20%, with larger regional reductions, especially at high latitudes. In extreme worst-case setups with strong solar storms superimposed on a weak field, local depletions could be deeper still, approaching the kind of losses we associate with the modern Antarctic ozone hole, at least for short periods. If that were literally true everywhere, all the time, life at the surface would feel it. More UVB reaching the ground means more damage to DNA in exposed organisms. Plants near the surface of lakes, algae drifting near the top of the ocean, unshaded skin and eyes on land animals, all of them would face an uptick in stress. Over generations that could alter ecosystems, more pigments, more protective structures, more selection for behaviors that avoid harsh midday light. But as often happens in science, the closer people looked, the more complicated the story became. Later models were a bit more restrained. They folded in better reconstructions of the geomagnetic field, more realistic solar behavior, and more detailed chemistry. They looked not just at how much ozone is destroyed, but at how fast is it replenished, and how the circulation of the stratosphere shuffles air around the planet. In those runs, global mean ozone loss during Laschamps still exists, but it's modest. Maybe on the order of a few to 10% over broad regions, with patchier, stronger depletions in some latitudes and seasons, enough to bump up surface UVB by a comparable or slightly larger factor, especially under clear skies at high latitude. Serious for organisms living right at the edge of tolerance, but not a sterilizing flash. And then there's climate. Ozone isn't just a sunscreen. It's a greenhouse gas and a source of heat in the stratosphere. Strip some of it away and you cool that layer. That can in turn tweak jet streams, change patterns of high and low pressure, and ripple down into surface climate. Add to that the fact that particle-driven chemistry also makes nitrogen oxides, which can act like a fertilizer when they eventually wash out of the air and land on soils or the ocean, and you have a web of possible feedbacks. So modelers tried the next question: does the Laschamps ozone perturbation show up as a clear climate signal? Here, the results get even more cautious. Some simulations hint at small regional coolings or warmings, shifts in precipitation patterns measured in a few percent, changes to the strength or position of storm tracks. Perhaps a bit more cooling over some continents, a nudge that might slightly deepen wintertime temperature drops in certain latitudes. But the amplitude of these changes is small compared to what the climate system was already doing on its own 41,000 years ago. This is the part that matters for interpretation: context. The Laschamps Excursion didn't happen during some calm, stable, Holocene-like climate. It unfolded in the middle of the last glacial period, a time when ice sheets waxed and waned, sea levels stood tens of meters lower than today, and the climate system was prone to its own wild swings. Ice cores from Greenland and Antarctica show abrupt warming and cooling events in that era. Dansgaard-Eschger events in the north, Antarctic isotope stage shifts in the south. Temperatures over Greenland could jump by 5 to 10 degrees Celsius in a few decades, then slide back down. Ocean circulation in the North Atlantic wobbled, affecting how heat moved around the planet. Dust levels changed. Monsoon systems strengthened and weakened. Against that restless backdrop, teasing out the fingerprint of a geomagnetic excursion is like trying to hear a flute line inside a thunderstorm. There are intriguing hints. Some records show changes around the time of Laschamps, slight shifts in rainfall patterns inferred from cave deposits, variations in dust flux, wiggles in temperature proxies. It's tempting to line them up with the drop in magnetic field strength and say, that's the climate responding to ozone loss and particle-driven chemistry. But timing in paleoclimate is tricky. Dating uncertainties of even a few hundred years can scramble alignments. Two things happening around 41,000 years ago are not automatically cause and effect. Ice sheet dynamics, volcanic eruptions, internal ocean variability, orbital cycles, all of these were also in play. That's why researchers are careful, or at least they try to be. One camp argues that the geomagnetic excursion probably did have some climate influence, but as a secondary player. In that view, particle-driven ozone changes and a slightly altered radiation budget nudged a system that was already near various tipping points. Maybe they made some regional transitions a little more likely, or changed the timing of a few events by decades or centuries, but they didn't rewrite the glacial script. Another camp is even more conservative. From their perspective, the Laschamps signal in climate proxies is either absent or indistinguishable from background noise. If you didn't know there had been a magnetic excursion, they argue, you'd be hard-pressed to discover it just by looking at temperature, rainfall, or ice volume records. For them, the main legacy of Laschamps is in cosmogenic isotopes and magnetic minerals, not in the climate itself. And then there are those who lean the other way, at least as a thought experiment. They point to the biggest chemistry models, the ones that generate sizable ozone losses under particular solar conditions, and ask what that might look like on the ground. A world with more UV stress, maybe slightly cooler in some high-latitude winters, perhaps a bit drier or wetter in certain belts. They note correlations between magnetic field changes and some paleoclimate features and suggest that, even if the case isn't proven, we shouldn't dismiss the possibility of a stronger link. Running through all of this is a methodological caution. Correlation is cheap, causation is expensive. It's easy to line up graphs and see patterns. Magnetic intensity drops here, a stalagmite growth rate changes there, an ice core proxy wiggles somewhere else. Our brains are wired to connect them, to weave a story where one thing causes another. But establishing that link requires more than visual synchronicity. It demands mechanisms that make physical sense, models that reproduce both timing and magnitude, and independent lines of evidence that point to the same conclusion. Right now, for Laschamps, the safest summary looks something like this. The weakened magnetic field almost certainly increased particle access to the atmosphere and altered upper atmospheric chemistry. That chemistry likely reduced ozone to some degree, especially at high latitudes, and slightly boosted surface UV in at least some regions. Those changes in turn may have had subtle effects on climate and ecosystems, but those effects were folded into a glacial world already dominated by ice sheets, ocean circulation shifts and orbital pacing. To the humans and animals alive then, did it feel like a distinct event? Probably not in the way we'd like to imagine. No sudden global shock that everyone would have noticed at once. More likely it was part of the background, a slightly different sky, a marginally harsher radiation environment, maybe small shifts in where plants thrived best, which roots herds preferred, how comfortable it felt to linger under the midday sun in certain regions. To see how those subtle physical changes might have intersected with actual lives, we have to step down from the stratosphere into the day-to-day world 41,000 years ago. Ice sheets grinding south, steppe and forest trading places, Neanderthals and early modern humans moving through a landscape that was changing for many reasons, not just because the compass had lost its way. Imagine you wake up as a human being 41,000 years ago. There are no cities, no farms, no written words, but the world is far from empty, and it is anything but simple. We're in the late Pleistocene, deep in the last ice age, not at the absolute coldest point that will come 10 or 15,000 years later, but solidly in glacial territory. If you could see the planet from far above, it would look strangely out of proportion. Over North America, a white shield of ice sprawls southward, hundreds to thousands of meters thick. The Laurentide and Cordilleran ice sheets cover most of what is now Canada and push down into what will one day be the northern United States. In Europe, the Fennoscandian ice sheet sits like a frozen crown over Scandinavia and parts of northern Germany and Russia. Glaciers spill out of mountain ranges, the Alps, the Pyrenees, the Caucasus, the Rockies, the Andes, feeding outwash plains and braided rivers. So much water is locked up as ice that sea level is tens of meters lower than it is today. The coastline, on a modern map hasn't been drawn yet. Continental shelves are dry land. The North Sea is mostly a broad, cold steppe where rivers meander toward a distant Atlantic. Britain is not an island, it's part of mainland Europe, connected by a windswept plain that herds of animals and small bands of humans cross on foot. In Southeast Asia, the shallow seas between many islands are dry. Great Sunda is a continuous landmass linking what will become Sumatra, Java, Borneo, and the Asian mainland. New Guinea and Australia are fused into a single continent. Sohul, ringed by reefs, mangroves, and rougher shores. Between the big ice sheets and the subtropics lies a vast belt of cold grassland and shrub, sometimes called the Mammoth Steppe. It stretches from Western Europe across Eurasia, into Beringia, and down into parts of North America. Long winters, short summers, strong winds, sparse trees. Think of a treeless prairie, but colder, drier, and more extreme. In some regions, dust storms sweep across the land as glacial winds scour exposed sediments and dump fine particles downwind. Farther south, the picture softens, but only a little. In the Mediterranean, in parts of the Middle East, in pockets of Africa and Asia, forests cling to wetter zones along rivers and coasts. Savannas and open woodlands pulse with the seasons, expanding and contracting as rainfall shifts. The tropics are not the dense, unbroken jungles of your imagination. Many are mosaics, patches of forest, scrub, grass, and swamp, constantly rearranged by climate swings, fire, and the movement of animals and people. This is the physical stage on which our story plays out. Now fill it with life. At 41,000 years ago, our species, Homo sapiens, is no longer confined to a single region in Africa. Modern humans have already begun their great expansion. Genetic and archaeological evidence suggests that by this time, Homo sapiens is established across large parts of Africa and is present in the Levant and much of Western Eurasia. There are modern humans in the Middle East, in Europe, in parts of Central and South Asia. Some have already reached Australia and New Guinea. Others are moving along coasts, up river valleys into colder latitudes at the edge of the ice. But we're not alone. Across much of Europe and Western Asia, Neanderthals are still there. They've occupied those landscapes for hundreds of thousands of years. Thick-boned, powerful, cold-adapted hunters with their own cultures, their own traditions. They know the caves, the valleys, the migration routes of the animals in intimate detail. They have survived earlier glacial swings, earlier pulses of cold and warmth, earlier shifts in vegetation. In parts of Asia, traces of another lineage still flicker. The Denisovans, those genetic ghosts identified from a handful of bones and teeth, are likely gone or dwindling by 41,000 years ago, but their legacy is not. Their DNA persists in some populations of Homo sapiens who have already interbred with them. Genes that help with high-altitude living in Tibet, or with processing certain kinds of food in parts of Asia and Oceania, are souvenir fragments of those encounters. So, the human world at 41,000 years ago is not a single, unified thing. It's a patchwork of small, mobile groups belonging to different human lineages. Modern humans in Africa and beyond, Neanderthals in Europe and Western Asia. Possibly the last shadows of Denisovan-like groups in parts of Asia. These populations don't cover the map evenly. They cluster around rivers, coastlines, resource-rich valleys and ice-free corridors. Around them, the animal world is both familiar and alien. On the mammoth steppe, huge herbivores dominate. Woolly mammoths and woolly rhinoceroses graze on tough grasses and sedges. Bison and wild horses move in large herds. Giant deer with antlers like living trees pick their way through open woodland margins. In North America, there are mastodons in forested zones, camels and horses on open plains, giant ground sloths in some regions, saber-toothed cats, and short-faced bears stalking the edges. In Europe and Western Asia, Neanderthals and modern humans hunt reindeer, red deer, steppe bison, horses, ibex, and sometimes the larger, more dangerous megafauna. In Africa, elephants, hippos, antelope, zebras and buffalo graze and browse across savanna and woodland, shadowed by lions, hyenas, leopards and wild dogs. In Australia, New Guinea, some of the giant marsupials diprotodons as big as small cars, massive kangaroos, giant birds are still present or only recently gone, sharing the landscape with the first human settlers. Life here is not gentle. Ecological pressures are intense. Winters in mid to high latitudes are long, dark and brutally cold. Food availability swings with the seasons. Animals must migrate, hibernate, or die. Humans must follow herds, store food, or find alternative resources. Small shifts in temperature or rainfall can move the boundary between forest and steppe by hundreds of kilometers, change the routes grazers prefer, modify when and where rivers flood. Predation risks are everywhere. A slight misjudgment on a mammoth hunt, a stumble near a cliff, a surprise encounter with a big carnivore can wipe out a significant fraction of a band. Disease, though less tied to dense populations than it will be in agricultural times, still lurks in parasites, wounds and contaminated water. Fire, both natural and human set, can transform a landscape in a day, turning forest to ash and opening new ground for grass. For humans, this means constant adaptation. Some groups focus on large game hunting, coordinating drives, learning seasonal patterns. Others increasingly rely on smaller animals, fish, shellfish, nuts, roots and seeds. Tools are diversified: stone points, scrapers, burins, bone needles, awls. Clothing from stitched hides. Shelters built from wood, bone and turf are now part of the toolkit, especially in colder regions. Symbolic behaviour, ornaments, pigments, engravings is already present in both Neanderthals and Homo sapiens, though it varies by region. From a modern scientific perspective, this time slice is almost overrepresented and underrepresented at the same time. On one hand, 41,000 years ago sits in an archaeologically rich zone. The last glacial period, especially its later half, has left abundant traces in caves, rock shelters, lowest deposits and lake sediments. Bones, tools, hearths, ochre, beads, carved objects, they all show up in layers we can often date with radiocarbon. In Europe, for instance, this is the era of the so-called Middle to Upper Paleolithic transition, when Neanderthal-associated industries overlap with and are gradually replaced by those associated with incoming or expanding Homo sapiens. In Africa, there are late Middle Stone Age and early Later Stone Age industries. In Australia and parts of Asia, we have evidence of early human occupation in caves and along coasts. On the other hand, the record is still fragmentary and uneven. Glacial ice wipes clean huge areas, grinding away any traces that once existed. Rising and falling sea levels drown and expose coastal sites. Many of the most promising, resource-rich shorelines from 41,000 years ago are now under tens of meters of water. In regions without caves or good sediment traps, artifacts weather away, wash downstream, or are buried beyond reach. Radiocarbon dating becomes fuzzier as you approach its upper limits, and many contexts we care about lie right around that edge. Even where we have sites, they represent pinpricks in an enormous landscape. A single cave with a beautiful stratigraphy may stand in for thousands of square kilometers, where nothing was preserved. So we end up with a mosaic full of gaps. Here, a well-documented Neanderthal campsite in a French valley. There, a Homo sapiens hunting camp on a Central Asian plain. A shell midden on an Australian coast. A rock shelter with ochre and engraved pieces in southern Africa. We can infer patterns of movement, diet, technology, and social life, but always with the knowledge that we are seeing only the pieces that escaped erosion, ice, and time. Into this already complex world, the Laschamps Excursion arrives. Not as a single obvious catastrophe, but as a multi-thousand-year episode in which the planet's magnetic field weakens, wanders, changes shape, and then recovers. The weakened field lets more high-energy particles into the atmosphere, tweaks ozone, alters the pattern of auroras, and raises surface radiation slightly, especially at higher latitudes. How does that intersect with the lives of the beings we've just met? For a Neanderthal band wintering near the edge of the European ice sheet, does a slightly different sky change when they travel, where they camp, how well their eyes cope with snow glare? For Homo sapiens groups moving along Asian coasts, does a modest increase in UV make midday more uncomfortable, or favour boats leaving at dawn and dusk? For plants, plankton and animals already stressed by glacial climates, does the extra radiation tip the balance in subtle ways, nudging some species up and others down? These are the questions that sit at the boundary between geophysics and archaeology, between magnetic field lines and hearth ashes. To approach them, we need to look not just at maps of ice and coastlines, but at actual people and places, caves streaked with soot and red ochre, bones bearing cut marks, layers of ash and charcoal laid down year after year, while the compass above their heads was quietly forgetting where north should be. If you open a textbook, it can be tempting to tell a clean story. The magnetic field almost collapses around 41,000 years ago. Neanderthals disappear from most of Europe not long after. Modern humans expand. Therefore, the sky flickers, the shielding fades, one kind of human struggles, another thrives. It sounds neat. It's also almost certainly too neat. Researchers who try to connect the Laschamps Excursion to human history tend to circle around a cluster of related ideas. None of them are as simple as radiation kills Neanderthals. But they share a theme. A weakened magnetic field adds just enough extra stress, over just enough time to matter in a world already on the edge. One line of thinking starts with habitats. If the field weakens, more charged particles reach the atmosphere. ozone thins in some regions, ultraviolet light at the surface creeps up. Not dramatically everywhere, but measurably, especially at mid to high latitudes where Neanderthals are concentrated. Now picture that mammoth steppe again. Plants here already live close to their tolerance limits. Short growing seasons, frost, drought, wind. Add a slight increase in UV, and you might shift which grasses dominate, which shrubs set seed successfully, which trees cling to south-facing slopes instead of north-facing ones. Not a uniform die-off, but a rearrangement of the mosaic. Herbivores follow the changes. Their favourite grazing grounds shift north or south, uphill or down. Rivers bordered by willow and poplar one century might favour different species the next. For human hunters depending on predictable migrations, even modest shifts in plant communities can ripple outward. Herds take different routes, arrive earlier or later, linger in unfamiliar valleys. In this view, the magnetic excursion doesn't target Neanderthals directly. It perturbs the background, vegetation, snow cover, productivity of the land, and that, in combination with ongoing Ice Age climate swings, pushes some regional populations into trouble. Another idea focuses on demographics. Small, scattered bands of humans are vulnerable to runs of bad luck. A few harsh winters, a few failed hunts, a disease outbreak, and a local lineage can disappear. If the Laschamps Excursion coincides with a cluster of environmental challenges, cold snaps, droughts, more frequent storms, then it might act like one more weight on the scale. Neanderthal populations at this time already seem fragmented. Genetic studies of Neanderthal remains show low diversity, signs of inbreeding in some regions and evidence that local groups were sometimes quite isolated. That's the kind of population structure that doesn't handle extra stress well. Modern humans, by contrast, may have been operating with denser social networks, more frequent exchange of mates and materials between bands, and a broader toolkit of foods and technologies. In that case, the same environmental perturbation could hit both species, but one has more redundancy built into its social system. When things go wrong, there are more allies, more options, more ways to move. So you can sketch a plausible pathway from a weakened magnetic field to subtle environmental shifts to differential survival between Neanderthals and Homo sapiens. But then the evidence starts arguing back. First, timing. Neanderthals do not vanish in a single moment. Their decline is regionally staggered. Some areas of Western Europe may lose Neanderthal populations earlier, others hold on longer. In the Iberian Peninsula, Neanderthal-like industries and fossils seem to persist after 41,000 years ago. In parts of Eastern Europe and Western Asia, the overlap between Neanderthals and incoming modern humans stretches across thousands of years. Modern humans don't sweep across Eurasia at the exact moment of the excursion either. Some Homo sapiens groups are present in the Levant and beyond before Laschamps. Others arrive in Europe as the excursion is ending or already past. The demographic transition from a Neanderthal-dominated Europe to a Homo sapiens-dominated one is a drawn-out, patchy process. On the geophysical side, dating the excursion itself carries uncertainties. Different archives, lava flows, deep-sea sediments, lake cores, record slightly different timing for when the field weakened, when it reached its minimum, when it recovered. Radiocarbon calibration curves that rely on cosmogenic nuclides like beryllium-10 and carbon-14 bring their own error bars. Put those uncertainties on top of the radiocarbon age ranges for bones, tools and cave layers, and the neat alignment starts to smear. Instead of a single sharp moment, you get overlapping bands of probability. Sometimes the Laschamps Excursion and key archaeological transitions seem to coincide. Sometimes they slide past each other. Second, alternative explanations for Neanderthal decline are not in short supply. One of the most widespread is simple ecological competition. Modern humans arriving in Neanderthal territories bring slightly different hunting strategies. perhaps more flexible diets, denser social networks, and, eventually, more elaborate symbolic practices. They might hunt the same animals, but with different scheduling, different sharing rules, different ways of storing and processing meat. They might exploit fish, birds, and plant foods that Neanderthals use less intensively. In this scenario, Neanderthals don't lose because the sky changes. They lose because another population carrying a different package of genes and culture outcompetes them over generations. Disease is another candidate. Close contact between two human lineages that have been separated for hundreds of thousands of years could allow pathogens to jump into immunologically naive hosts. Even a modest uptick in mortality, especially among infants and mothers, could devastate small, already stressed populations. The archaeological record would not easily preserve such epidemics. Bones do not carry most viruses, and ancient DNA for pathogens this old is rare. Interbreeding itself also plays a role. Genetic studies show that Neanderthals didn't simply vanish into the void. A portion of their DNA survives in modern non-African humans. That implies not just coexistence, but mating and gene flow. Over time, with modern humans vastly outnumbering Neanderthals, that gene flow can look like absorption. Neanderthals as a distinct cultural and anatomical tradition fade, but pieces of their genome persist, diluted into a much larger Homo sapiens population. Climate variability, independent of magnetism, is yet another factor. The last glacial period includes rapid climate oscillations, abrupt cooling and warming events that reorganize ecosystems in decades to centuries. These Dansgaard-Eschger events, seen in Greenland ice cores, line up roughly with some archaeological shifts in Europe and Western Asia. That offers another way to link environmental instability to Neanderthal fortunes without invoking the magnetic field specifically. To claim that Laschamps played a decisive role, scientists would need a particular kind of evidence. They would need tight chronological correlations between the excursion and demographic changes, not just at one site, but across many regions. They would need to show that population declines or cultural transitions cluster in the window of maximum field weakness more than they do in adjacent periods. They would want biological signals, perhaps elevated mutation rates, in ancient DNA from organisms living at high latitudes during Laschamps, relative to similar organisms before and after, or characteristic damage patterns in DNA that match what high-energy particles produce. So far, those signals are subtle at best and confounded by the normal decay that affects genetic material over tens of thousands of years. They would benefit from clear ecological fingerprints, pollen records that show plant communities shifting in ways best explained by increased UV or altered atmospheric chemistry during the excursion, marine records where plankton or productivity changes align with cosmogenic peaks, and then map onto changes in coastal human sites. And all of this would have to survive the known complications. Radiocarbon ages that blur over centuries, different cave layers that have mixed slightly over time, genetic samples that come from a handful of individuals standing in for vast unseen populations. Regional differences, where one valley might show stress while another, with better shelter or richer resources, sails through. When you put it all together, the picture that emerges is not a crisp line of cause and effect, but a tangle of influences. The Laschamps Excursion definitely happened. It definitely altered the flow of radiation into our atmosphere. It likely had some environmental consequences, and those consequences unfolded while Neanderthals and modern humans were sharing a continent and adjusting to each other's presence. Whether it nudged Neanderthals closer to the edge, or barely registered in their day-to-day reality, remains an open question. What we can say is that the timing is intriguing, the mechanisms are plausible in outline, and the story is not settled. In a world of small populations and narrow margins, even modest changes in the sky above could matter. But the decline of Neanderthals and the rise of Homo sapiens in Eurasia look to be the product of many overlapping processes: climate, competition, culture, chance. And while scientists argue over graphs and error bars, the people living through it were dealing with a simpler calculus. Stay warm, find food, keep children alive, remember the paths, remember the seasons. For clues about how they met those challenges under a restless sky, we turn from global fields and ice cores back to the places where their lives actually unfolded. The caves, the pigments, the layers of ash and soot where humans, Neanderthal and modern, may have sheltered not just from wind and cold, but perhaps in some small way from the changing heavens above. If you've spent your whole life under an open sky, a cave is a strange thing. From the outside, it's just a dark mouth in the rock. Inside, the temperature steadies, the wind dies, the sound of the world goes quiet. The weather can rage all it likes. A few meters of limestone don't care. For a creature trying to survive an ice age, that alone makes caves valuable. But during something like the Laschamps Excursion, caves may have offered another, less obvious kind of refuge. Rock is a good shield. A few meters of stone overhead can cut down cosmic radiation significantly. Even the simplest models show that being underground, or even just beneath a thick overhang, reduces the flux of high-energy particles and some of the secondary radiation that cascades through the atmosphere when the magnetic field weakens. Now, to be clear, no one is imagining Neanderthals and early Homo sapiens discussing magnetic shielding over the fire. What matters is not the theory, but the behaviour. If the sky is a little harsher, more ultraviolet on bright days, perhaps more frequent storms, more flickering auroras at mid-latitudes, then the safest, most comfortable places might happen to be the ones with stone over your head. Caves concentrate many of the things you'd want in unstable times: protection from wind, storage for meat, dry floors, places to raise infants away from predators, and, as a side effect, some shielding from whatever is happening above the clouds. So, when archaeologists notice that around this general period, caves and deep rock shelters in Europe and Western Asia start to show more intensive occupation, more layers of ash, more tools, more repeated use over centuries, it's tempting to wonder. Was this partly a response to a changing sky? We don't know. What we can say is that caves became central theatres of human life and symbol during the last glacial cycle. Places like Chauvet, Lascaux, El Castillo, Altamira, and many less famous sites preserve an archaeological echo of that shift. Inside these caves, on walls that had never seen sunlight, people started leaving marks. Hand stencils made by blowing pigment around outstretched fingers. Animal figures, bison, horses, mammoths, lions, painted with a confidence that still feels uncanny tens of thousands of years later. Abstract signs, dots, lines, ladders, branching shapes. In some sites, the earliest of these artworks cluster roughly between 45 and 35,000 years ago, bracketing the time of the Laschamps Excursion. At the same time, we see another thread winding through the record: ochre. Iron-rich earth, ground into powder, mixed with fat or water, smeared on skin, objects and walls. Red, yellow, brown. Ochre shows up in African sites long before Laschamps. There are pieces with grinding facets and scrape marks dating back hundreds of thousands of years. But in Europe and Western Asia, its use becomes more visible just as modern humans, and the last Neanderthals move through landscapes that have seen the magnetic field flicker. Some Neanderthal sites show traces of pigment, possible body decoration, perforated shells that may have been strung as ornaments. Early Homo sapiens sites show similar habits, sometimes in greater abundance. Pigments appear on tools, in burials, splashed on cave walls. It's easy to spin stories here. Red ochre as sunscreen under a stronger UV sky. Pigment stripes as practical protection as well as symbol. Caves chosen specifically because they shielded from cosmic rays. Those are possibilities. They're also hard to test. Humans use ochre for many reasons: to mark group identity, to adorn bodies for rituals, to help tan hides, to dry and preserve food, to create adhesives, to paint stories on walls. All of these can coexist. And the rock art that blooms in some caves after 45,000 years ago likely has its own tangled causes: growing symbolic capacity, social signalling between groups, new mythologies carried by Homo sapiens into old Neanderthal territories. When you live in a world of overlapping stresses, ice age climates, shifting herds, new neighbours with different tools, the urge to tell stories on stone may not come from one trigger, but from all of them together. Even figuring out exactly when people used a cave, or when they painted a particular animal, is more difficult than it sounds. Archaeologists have a small toolkit for dating cave life. They can date charcoal from hearths using radiocarbon, giving ages for when fires burned in particular layers. They can analyse the sediment, the slow rain of dust, ash and tiny fragments of bone that accumulates on cave floors, building up a stratigraphy of occupation and abandonment. For the art itself, they sometimes date tiny crusts of calcite that grew over or under a painting using uranium-thorium methods. If a mineral skin forms on top of a red dot, the age of that skin gives a minimum age for the paint beneath. Each method comes with its own uncertainties. Charcoal can be older than the fire it's used in, especially if someone pulled a dead branch from a centuries-old tree. Sediments can slump, mix, or be disturbed by burrowing animals and later visitors. Calcite grows at uneven rates. A flake the size of a fingernail may represent a thin slice of time or many centuries. Radiocarbon calibration curves themselves bend and kink because of changing atmospheric chemistry, including, ironically, changes influenced by events like the Laschamps Excursion. When you stack all those error bars, the timeline blurs. A hand stencil might be 41,000 years old, or 39, or 43. A hearth layer in the same cave might straddle the Laschamps window, or sit just before or just after. This is why careful researchers are cautious. There is a temptation to point at a span of dates and say, here, this is when the field was weakest, this is when cave use increases, this is when art appears, therefore cause and effect. Instead, many talk about a behavioural response hypothesis. The idea is modest. If the magnetic field weakens and environmental stresses nudge upward, slightly more UV here, slightly more storms there, then humans might respond by adjusting behaviour, spending more time in caves and rock shelters, scheduling activities differently, using pigments more, decorating bodies and tools in ways that strengthen identities and alliances when times are hard. Under this view, the Laschamps Excursion is one ingredient in a stew of pressures. It doesn't have to be the chef. Ice Age climates were already volatile. Herbivore populations rose and fell. New human groups were moving into old territories. Disease, competition, interbreeding, and plain bad luck all played their parts. Any one cave bears witness to only a tiny piece of that world. What we see in the archaeological record, especially in caves, looks less like a single dramatic reaction and more like a layered adaptation. People hedge their bets. They cluster in places with stable temperatures and good vantage points. They build fires in the same sheltered hollows again and again. They decorate themselves and their surroundings, turning stone ceilings into shared memory palaces. They develop habits of where to sleep, how to store food, what colours to wear, that make sense in a world where danger can come from the weather, from predators, from neighbouring bands, and perhaps quietly from above. By the way, if you'd like to go deeper into this kind of slow, winding human story, the book that inspired this series is available at sleepytimehistory.com, and there's a discount running this week. Taken together, the caves and the ochre, the hearths and handprints suggest that our ancestors were not passively waiting for the sky to calm down. They were doing what humans always do, stacking small advantages. A little more shelter, a little more cooperation, a little more meaning painted on the walls to bind a group together when the outside world feels unpredictable. Whether or not the Laschamps Excursion directly pushed them underground, it unfolded in a world where humans had already learned a crucial trick. When the environment throws multiple problems at you at once, you don't search for a single solution. You weave a net of many small ones. That net, social, technological, symbolic, would matter not just for those huddled in European and Asian caves, but for the other creatures sharing their world, many of whom depended on cues we rarely notice. Because while humans could choose to duck into stone and firelight, countless animals navigated the same restless sky with a different kind of compass entirely. Out there beyond the mouth of the cave, the world was full of quiet navigators. They didn't carry maps, they didn't name constellations, but they moved year after year along paths so consistent that you can still draw them on a globe today. Flyways arcing from Siberia to Africa, whale routes winding through the world's oceans, salmon lines threading from rivers to sea and back again. Many of them were listening to something we can't feel at all. Magnetoreception. If you strip it down to the barest idea, it's simple. Some animals can sense Earth's magnetic field, and they use that sense as one more piece of information about where they are and which way they're going. Migratory birds are the classic example. Take a young bird raised in a planetarium, show it the right autumn stars, and it will try to fly in the normal migratory direction. Twist the simulated magnetic field around that bird, and its preferred direction twists with it. Redirect the invisible lines of force, and the bird's internal compass follows. But birds are not alone. Sea turtles released far from home correct their course in ways that only make sense if they're reading magnetic signposts in the ocean. Some fish, including salmon and trout, seem to imprint on the magnetic conditions of their natal rivers. Even certain bacteria grow tiny chains of magnetic crystals inside their cells, using them like microscopic compass needles to line up with the field. How they do this is one of those scientific puzzles that's mostly solved and still mysterious at the same time. There seem to be at least two main systems. One uses magnetite, iron-rich crystals with strong magnetic properties. These crystals form in special cells or structures and physically tug or align in response to Earth's field. In some animals, especially those navigating in dark or murky environments, these magnetite particles probably act like literal compass needles, pointing north-south and giving the brain a simple directional cue. The other system is stranger. In the eyes of many birds, there are light-sensitive proteins called cryptochromes. Under the right conditions, they can form radical pairs of electrons whose behavior depends on magnetic fields at the quantum level. Experiments suggest that in certain wavelengths of blue-green light, the animal's visual system might see a faint pattern, an overlay or filter shaped by the magnetic field. In other words, direction may appear as a subtle glow or shading in the bird's field of view. It's as if north and south are not just directions but colours. Now imagine living in a world where that colour is stable, year after year. Migration routes, homing behaviours, daily commutes between feeding and nesting areas, over hundreds of thousands of generations, they all tune themselves to that invisible pattern. Then, briefly, the pattern starts to wobble. During the Laschamps Excursion, Earth's magnetic field didn't just weaken, it became more complicated. The dipole, the simple bar magnet part with a clear north and south, lost much of its strength. In its place, paleomagnetic reconstructions suggest a more tangled structure. Extra poles, local patches of reverse direction, zones where the field lines kinked in unexpected ways. For a creature relying heavily on the magnetic field, that would feel less like a gentle adjustment and more like driving a familiar road while the street signs keep rotating. So what might that have meant for the animals sharing the Pleistocene world with Neanderthals and early Homo sapiens? For long-distance migrants, birds, whales, sea turtles, the key issues would be twofold: field strength and field geometry. If the field becomes much weaker, the difference between correct and incorrect direction shrinks. The signal-to-noise ratio drops. Any internal compass based on tiny magnetic forces has a harder time standing out against random fluctuations and biological noise. If the field becomes more chaotic, its geometry, how lines of force angle into the ground, how intensity varies across latitude, changes in ways that don't match ancestral experience. A bird that normally expects the field to get stronger as it flies poleward and weaker as it flies toward the equator might suddenly encounter pockets where that gradient reverses or stalls. A turtle using subtle differences in inclination to know how far north or south it has drifted might read a position that no longer maps cleanly onto the coastline it remembers. In the simplest picture, you would expect more navigational error. Migration routes might become fuzzier bands instead of tight corridors. Arrival dates might spread out as some individuals overshoot, undershoot, or take longer, more meandering paths. Some species could see higher juvenile mortality if inexperienced animals, lacking strong inherited maps, get lost more easily. But that's the simple picture. Reality is messier, and for the animals, probably kinder. Very few species rely on magnetoreception alone. Birds also navigate using the position of the sun, patterns of polarized light in the sky, star constellations at night, landmarks on the ground, smells, wind direction, and even infrasound from distant oceans and mountains. Salmon pick up chemical signatures in rivers. Whales may use underwater topography, temperature gradients, and social learning. Even tiny insects like monarch butterflies combine a time-compensated sun compass with internal clocks, and perhaps magnetic cues. Magnetoreception is more like one instrument in a band than the whole orchestra. When that one instrument goes off-key, because the field is weak or twisted or briefly reversed, animals can and do lean more heavily on the others. We know this from modern analogues. Volcanic rocks and iron-rich formations create local magnetic anomalies where the field points in odd directions or has unexpected strengths. Humans only discovered some of these because aircraft compasses behaved strangely over them. Yet birds still migrate through these regions. They may detour a bit. They may put more weight on visual landmarks or the sun, but the migrations don't collapse. Solar storms can also temporarily disturb the magnetic field. During strong geomagnetic storms, the field can pulse and ripple over hours to days. Radio communications fuzz, auroras bloom farther from the poles, low Earth orbit satellites feel extra drag. Migratory birds flying through such nights sometimes show increased scatter in their headings. They reorient when the storm passes. There are even studies where researchers fit birds with small magnets or coils that distort the local field around the animal. The birds get confused at first, especially in overcast conditions. When other cues are available, though, many eventually manage to orient correctly anyway. All of this suggests that while a weakened and scrambled field 41,000 years ago could have made life harder for magnetic navigators, it probably didn't turn the world into pure chaos. Instead, it likely added friction. More young birds losing their way on their first migration. More turtles taking suboptimal paths. Slight shifts in where herds of caribou or reindeer or their Pleistocene equivalents tended to travel if they were using any magnetic information at all. Indirectly, that might have mattered to the humans and Neanderthals watching the herds, because animal movements shape hunter movements. But here we run into a hard boundary. We do not have direct evidence of migration disruption tied specifically to Laschamps. No fossilized goose with a note pinned to it saying, "Got lost, field too weak." No layered record of stranded whales dated neatly to the excursion. What we have are modern experiments and observations of animals under disturbed magnetic conditions, plus models of what the field probably looked like 41,000 years ago. From those, biologists and geophysicists can sketch hypotheses. One possibility is that species with flexible multi-Q navigation systems rode out the excursion with only modest increases in mortality and error. Another is that species leaning more heavily on magnetoreception, especially long-distance ocean migrants, experienced a temporary drop in navigation success, enough to thin populations or shift breeding grounds slightly, but not enough to leave a clean, worldwide fossil signature. There's also the timescale to consider. Laschamps, even including its lead-up and recovery, played out over thousands of years. For a migratory bird with a lifespan of a few years, that's many, many generations. Natural selection can work quickly under those circumstances. Individuals with a stronger reliance on non-magnetic cues, or with slightly more robust magnetic sensors that still functioned in a weaker field, would leave more offspring. Behaviours could shift, routes could adjust. The migration systems themselves could evolve to cope with the scrambled compass. In that light, the excursion might look less like a single sudden disaster and more like a prolonged invisible pressure, a background challenge nudging populations toward greater navigational flexibility. From the vantage point of a human family tucked into a limestone shelter, the effect would have been indirect, if they noticed it at all. Perhaps some bird migrations became a little less predictable. Perhaps certain coastal rookeries or nesting cliffs were used less often, others more often. Perhaps some prey animals appeared in valleys where they had rarely come before, or vanished from old hunting grounds a bit sooner in the season. To the people watching, this would register as the same thing they were always tracking. The animals are shifting. The herds are late. The birds came early this year. The sea is different. They would respond the way they always did, by watching more closely, telling stories about unusual years, adjusting routes, building new knowledge on top of old. The magnetically guided lives around them would flex and adapt, just as the humans did. In a world where the sky's invisible lines were bending, the shared lesson across species was the same. You trust your compass, but you never trust only your compass. And for our ancestors, there was another question hanging just beyond that realization. If a scrambled field could tug at bird flocks and sea turtles, what might it do to a civilization like ours, whose own compasses, satellites and power grids quietly depend on the same restless field beneath the auroras? To imagine that, you don't have to change the physics. You just have to change the technology. Those Neanderthals and early Homo sapiens, watching faint curtains of aurora on the horizon, lived under the same basic rules. Charged particles from the sun, magnetic field lines guiding them, ozone absorbing what it could. What they didn't have were things that break when the sky misbehaves. We do. Our civilization has quietly wired itself into the interaction between the sun and Earth's field. It shows up in places you don't usually think about when you look at the night sky. Start with satellites. Every weather forecast, every GPS position on your phone, every time a ship navigates through fog in the Arctic using satellite signals, it's all relying on machines orbiting on the edge of that magnetic shield. When the magnetic field is strong and orderly, it helps keep Earth's radiation belts and upper atmosphere relatively stable. Strong solar storms still happen, but the protective bubble is thick. And satellites are designed with that in mind. Hardened electronics, safe modes, margins in their orbits. We know what happens when conditions get more extreme, because even in our current, still healthy field, the sun occasionally reminds us. In 2003, during the Halloween storms, satellites glitched, some instruments shut down, GPS accuracy degraded. In 2015, airlines rerouted polar flights to lower latitudes because radio communications in high-latitude airspace became unreliable. During big storms, auroras slide toward the equator and the upper atmosphere puffs up, increasing drag on low-orbit satellites and shortening their lifetimes unless engineers adjust. Now scale up the vulnerability, not by making the sun angrier, but by weakening the shield. A near-vanishing dipole means more high-energy particles can penetrate to lower altitudes and latitudes. The radiation belts could swell. The upper atmosphere could be more inflated more often. The same solar storms we shrug off today could become, in effect, larger from the satellite's point of view. Electronics in orbit would see more frequent radiation hits, single-event upsets where a bit in memory flips, or cumulative damage in sensitive components. Satellites we expect to last 15 years might last 10 or 5. GPS constellations would need more frequent replacement, more robust error correction. Earth observation, communications, navigation, all still possible but more expensive, more failure-prone, more work for the teams on the ground. Then there's the power grid. If you've ever seen a picture of long transmission lines stretching across a landscape, those seemingly quiet wires are, from the perspective of geomagnetic storms, antennas. When the magnetic field over a region wobbles quickly, because a wave of charged particles has hit the magnetosphere and set currents surging through the upper atmosphere, it induces electric currents in the ground. Those currents, in turn, leak into long conductors, pipelines, telecommunication lines, and high-voltage power lines. Under strong geomagnetic storms, these geomagnetically induced currents can saturate transformers, heat them, or trip protection systems. In March 1989, a storm knocked out power to much of Quebec in less than 2 minutes. Transformers elsewhere were damaged, some permanently. Again, that was with a field stronger than today's, and certainly stronger than during Laschamps. In a weakened field world, the same solar conditions would drive larger geomagnetic disturbances at the surface. The safe operating envelope for grids would shrink. Transformers would need redesigning, protection schemes, rethinking. Grid operators would have to treat space weather forecasts the way coastal cities treat hurricane forecasts, something you plan for, drill for, and occasionally shut things down for. None of this is unmanageable. It's just a different baseline. Aviation would notice too. High-altitude routes near the poles are convenient. Shorter great circle distances between continents, less fuel, less time. But those paths also cut through regions where Earth's magnetic shielding is thinnest, and where solar particles more readily pour into the atmosphere. On quiet days, that's fine. On stormy days today, airlines already reroute flights, both because radio communication in high-latitude bands can be disrupted, and because radiation doses to crew and passengers tick up a bit. In a world with a much weaker global field, those moderate storm days start to look more like today's major storms. Rerouting could become more common. Aircraft electronics would need extra shielding. Medical and occupational guidelines for frequent flyers and crew might become stricter. Even communications on the ground, the invisible web of radio waves and signals, would feel the change. Shortwave radio bounces off the ionosphere, that charged layer in the upper atmosphere, sculpted by both solar radiation and Earth's field. Navigation systems, long-distance communications, even some emergency networks depend on its behavior. A weaker, more chaotic field would mean a more variable ionosphere, more frequent disruptions, more blackout regions during storms where certain frequencies just don't get through. If all of this sounds like a disaster movie, it's important to slow down and place it in time. Field changes like Laschamps are not switches you flip overnight. The dipole didn't fall to a fraction of its normal strength on a Tuesday and come back on a Friday. The entire excursion, from the first significant weakening to the return of a stable, strong dipole, took on the order of thousands of years. The most extreme phase, where the dipole was really feeble, still lasted centuries. From a geological perspective, that's an eye blink. From a civilizational perspective, it's a very long planning horizon. Civilizations can destroy themselves quickly. But when the challenge is steady, incremental change, our species has a track record of adapting, building levees, changing crops, inventing vaccines, redesigning ships, and more recently, hardening the electrical grid when someone notices a risk. Scientists are not watching the field out of idle curiosity. There is a dense network of ground observatories measuring its strength and direction. Satellites map its structure around the globe. Archaeomagnetic and paleomagnetic records are constantly extended to understand how it's behaved in the deeper past. The picture that emerges from all of this is nuanced. Yes, Earth's field has been gradually weakening over the last couple of centuries by roughly 10% or so. Yes, there's a sprawling region over the South Atlantic where the field at satellite altitudes is particularly weak. The South Atlantic anomaly that already causes extra glitches and radiation hits for spacecraft passing through. But no, that pattern does not cleanly match what we see in the run-up to known reversals or excursions. The field has wobbled, grown and shrunk many times without flipping. Local anomalies come and go, declines in strength can reverse. When geophysicists compare today's behaviour to, say, the onset of Laschamps, they see some qualitative similarities, patchy regions, complex multipole patterns, but the timescales and trajectories do not let anyone confidently say, we are now entering another Laschamps. It could be the early stage of a larger rearrangement. It could be one of many medium-sized fluctuations that never become a full excursion. On human timescales, that ambiguity simply means we monitor, we model, we prepare for storms, and we live our lives. Even in the most pessimistic scenario, a deep weakening over the next few thousand years, we are not looking at an unshielded planet bathed in lethal radiation from one year to the next. The atmosphere itself, tens of kilometers thick, remains an excellent shield against most harmful solar and cosmic radiation. At sea level, radiation doses would rise somewhat, especially at high latitudes, but likely within a range that modern societies could manage with relatively modest changes. Adjusted flight routes, better shielding for certain occupations, more attention to high-dose events. The real vulnerabilities sit in our devices and infrastructure, and those can be redesigned. Power grids can be segmented and grounded differently. Transformers can be built with geomagnetic storms in mind. Satellites can carry more robust electronics and smarter safe mode protocols. Backup navigation methods using inertial systems, star trackers, even low-tech charts can complement GPS when it flickers. In other words, a near-vanishing field in a technological age is not so much an extinction threat as a very demanding engineering problem spread over many generations. If our ancestors at 41,000 years ago could adapt to a sky that glowed in unusual places and seasons without equations or satellites or even knowing what magnetism was, a civilization that can launch telescopes and model the core of the Earth has options. We do not need to picture the next excursion as a single night when every light goes out and never comes back. It is more realistic and more faithful to the geological record to imagine a long period of adjustment, space weather alerts becoming part of normal forecasts, satellites built like deep-sea submersibles for radiation instead of pressure, power companies treating the sun as one more stakeholder they have to listen to. The field has flickered before. Life passed through those intervals, not unscathed, but unbroken. As we lie here imagining compasses that forget north, it's worth letting that knowledge settle. We are already watching, already learning, already quietly adapting to a planet whose magnetic heart is never perfectly still. The story of reversals and excursions is not a prophecy of sudden doom. It is a reminder that even the deepest parts of Earth are restless, and that like the people in their caves beneath strange auroras, we'll meet that restlessness with our own kind of resilience. If you've made it this far into the story, there's one more layer that matters. Everything you've heard about Laschamps, about weakened fields and wandering poles and strange skies, comes from traces so faint they almost don't seem real. Magnetic whispers in cooled lava, tiny alignments in grains of dust at the bottom of the sea. Extra atoms of one isotope hiding among billions of others in ice and in wood. None of it is a finished picture. It's more like a sketch the planet keeps redrawing, and scientists keep tracing over each time with slightly sharper pencils. One of the main ways that sketch improves is simply by getting more of it. Every paleomagnetic record you've heard about, lava flows, lake muds, deep sea cores, is just one line of evidence at one place. To understand a global event like Laschamps, you need as many independent records as possible, spread across every continent and ocean, overlapping in time. So the work continues. Geologists drill new cores from the ocean floor, cylinders of sediment that settled grain by grain, while the field above them was doing strange things. They hike to remote volcanic provinces and sample ancient lava flows that cooled right in the middle of the excursion. They pull mud from small alpine lakes, peat from bogs, stalagmites from caves. Each sample is taken back to a lab and coaxed, gently, to reveal the direction and strength of the field when it formed. Not once, but at many depths, at many times, across many sites. The goal isn't just more data, it's better data, higher resolution. That means being able to say not just the field was weak sometime in this 10,000-year window, but it dropped sharply over a few centuries, or it flickered back and forth on 1,000-year scales. To do that, scientists pair paleomagnetism with increasingly precise dating methods. Radiocarbon dating gets recalibrated with tree rings. Tephra layers, thin bands of volcanic ash, tie different cores to the same eruption. Uranium-thorium dating pins down the ages of cave formations. In ice, annual layers can be counted like tree rings. In some lakes, too, winter and summer sediments build up visible couplets. The more anchors in time you have, the more you can align different records with each other. A sudden jump in field direction in a New Zealand lava flow might match a wiggle in a North Atlantic sediment core. A spike in cosmogenic isotopes in Greenland ice might line up with a weakening recorded in Chinese loess. When those independent clocks all tick together, confidence grows that you're seeing a real planetary event, not a local oddity. While this quiet, painstaking work goes on in labs and on ships, another group of scientists is doing something very different. They're trying to recreate the heart of the planet in equations. In their computers sit models of the geodynamo, the churning, convecting, electrically conducting liquid iron in Earth's outer core that gives rise to the field in the first place. They can't reproduce it perfectly. The real core is too large, too hot, too extreme. But they can capture its essential physics, set the rotation rate, set the heat flow from the inner core and the mantle, set the electrical conductivity and viscosity of the fluid. Then let the equations run. Out of that chaos, if the model is any good, a magnetic field emerges. It waxes and wanes, it drifts, sometimes it flips. These are not just pretty animations, they are hypotheses. Every time a model produces a reversal or an excursion, its pattern can be compared to the paleomagnetic record. Did the modelled poles wander in the same kinds of paths we infer from rocks? Did the dipole weaken by a similar amount? Did the event last as long? When the match is poor, the modellers adjust their parameters, or realise their assumptions were wrong. When the match is better, they still don't declare victory. They look for more tests. They try to reproduce not just one excursion, but the statistics of many. They ask whether the way the model's field recovers after an event looks anything like the way Earth's field has recovered in the last few million years. Validation in this context isn't a single yes or no. It's a long, quiet conversation between theory and evidence. And in that conversation, there are still lots of unanswered questions. We know in broad strokes that Laschamps involved a major weakening of the global dipole and a temporary dominance of more complex multipolar structures. But how did that look, place by place, on the surface? Were some regions actually better shielded during parts of the excursion, as magnetic flux concentrated in odd spots, while others were especially exposed. Did high latitudes always fare worse? Or did the geometry of the field sometimes put stronger pockets of protection over unexpected regions? Even the duration has fine structure we don't fully see yet. Was the field weak steadily for a few centuries, or did it sag, half recover, and sag again in pulses? Did the poles race around the globe in smooth loops, or in stuttering jumps? Some cores hint at rapid directional swings that might have played out on the scale of human lifetimes. Others smooth those swings out like a long exposure photograph. Then there's the coupling to the rest of the Earth system. We see correlations between Laschamps and spikes in cosmogenic isotopes. We see hints of climate anomalies in some regions. But cause and effect are hard to tease apart. Did changes in the magnetic field meaningfully alter atmospheric chemistry and climate? Or were they just one more nudge among many orbital cycles, volcanic eruptions, ocean reorganizations? Did regional climate responses depend more on geography than on magnetism? These are open questions, and scientists argue about them. Not in the sense of shouting, but in the sense of careful skepticism. One group publishes a result suggesting a strong climate impact of Laschamps in a certain region. Another group points out that the dating uncertainties overlap with a known shift in ocean circulation. A third suggests a different interpretation of the same isotopic signal. The picture doesn't collapse because of this. It sharpens. Interdisciplinary evidence is what holds it together. Paleomagnetists, isotope geochemists, modelers, atmospheric physicists, climate scientists, archaeologists, all of them bring different tools, different biases, different kinds of skepticism. A hypothesis about increased radiation at the surface isn't taken seriously until it's checked against both field reconstructions and chemical models of the atmosphere. A proposed link between Laschamps and a change in human behavior has to survive not just the magnetic timeline, but the archaeological one. Sometimes an exciting connection fades under scrutiny. Sometimes a subtle pattern seen in one core, dismissed as noise, reappears in another discipline's data and begins to look real. This is how understanding accumulates, layer by layer, like the sediments themselves. A century ago, we barely knew that Earth's magnetic field reversed at all. Mid-20th century scientists started to see crude stripes of polarity in ocean crust. By the time Laschamps was recognized as a distinct event, the idea that the field could nearly vanish and then recover in a few thousand years still seemed wild. Now we can talk about its approximate strength, its rough duration, its multiple peaks, even its fingerprints in ice cores and tree rings. In another century, if scientists keep drilling, measuring, modelling, arguing, the picture will be sharper still. Maybe they'll resolve century-scale swings we can only blur together tonight. Maybe they'll have models of the core that reproduce not just the broad statistics of reversals, but the details of specific events. What doesn't change is the theme: Earth's deep interior, the magnetic cocoon around the planet, the climate, the biosphere. They all change, often in dramatic ways. But our understanding of those changes also evolves, not in sudden revelations, but in overlapping waves of evidence. We live on a world whose magnetic heart can falter, reverse, and recover. We also live in a species that can notice, remember, and slowly decipher those episodes, long after the skies have gone back to normal. Layer after layer, record after record, model after model. The story of nights when the compass forgot north becomes less mysterious. Not because the planet is simple, but because patience can turn faint traces into something like a memory. By now, you can probably feel the shape of the story we've been tracing. A planet wrapped in an invisible magnetic shell. A field that does more than point compasses north. It steers charged particles from the sun. It helps hold our atmosphere in place. It quietly shields the surface from a flood of cosmic radiation. a field that 41,000 years ago lost its footing. During the Laschamps Excursion, the strong, simple dipole that were used to weaken dramatically, the north and south magnetic poles wandered far from their usual places. Other, smaller poles popped up and faded. For a little while, the field looked less like a tidy bar magnet and more like a tangled, shifting web. We don't see this directly, of course. We infer it from a whole stack of indirect clues. Rocks that locked in confusing directions as they cooled. Sediments whose tiny grains settled while the field above them leaned, slackened and twisted. Spikes in cosmogenic isotopes like beryllium-10 in polar ice and carbon-14 in ancient wood, telling us that more high-energy particles were reaching the upper atmosphere. From that web of evidence, a basic outline has emerged. Earth's dipole strength plunged to perhaps a few tenths of what it is today. In some reconstructions, at its weakest, it may have fallen to just a few percent. The deviations weren't a single sudden flip, but a complex dance lasting a few thousand years, with the most intense weakening compressed into something more like centuries. Above that flickering field, the sky would have been different. Auroras pushed toward lower latitudes. The atmosphere's chemistry nudged and disturbed as extra radiation split molecules and reshuffled ozone. Tree rings and ice layers quietly recorded the increased rain of cosmic particles. Somewhere under those skies, Neanderthals and early modern humans kept living their lives, hunting, gathering, painting in caves, seeking shelter when the weather turned harsh. Some parts of that picture are on firm ground. The Laschamps Excursion itself is as solid as anything in deep time science can be. Independent magnetic records across the globe agree that something dramatic happened to the field around 41,000 years ago. The cosmogenic isotope spikes line up with that timing, strongly suggesting a weakened shield and increased particle flux from space. We're also on reasonably safe footing when we say the field recovered. It did not stay weak forever. Over centuries to millennia, the dipole re-established itself. The poles drifted back toward more familiar positions, and the magnetic intensity climbed. Other parts of the story are much softer around the edges. Exactly how weak the field became in absolute numbers is still debated. Different reconstructions give different minima. The fine-scale timing, whether the weakening came in one sharp plunge or in several pulses, is still being refined as new, better-dated cores are added. The downstream impacts on climate and life are even more uncertain. There are intriguing hints. Correlations between the isotope spikes and regional climate shifts, suggestions of stress in some ecosystems, speculations about how changing skies and radiation might have nudged human behavior. But cause and effect are hard to untangle. Orbital cycles were shifting. Ice sheets were growing and shrinking. Oceans were reorganizing. Volcanoes erupted. Laschamps was one thread in a very complicated tapestry. If you imagine a spectrum from "we're almost certain" to "this is still an interesting idea," Laschamps itself, the weakening, the isotope fingerprints, and the eventual recovery sit at the more confident end. Detailed claims about global climate shocks, mass die-offs, or sudden leaps in human culture driven solely by the magnetic field belong closer to the speculative end. Possible, sometimes plausible, but not yet nailed down. And that's part of the quiet beauty here. We live at a time when we can even ask these questions. When faint magnetic memories in rocks, tiny extra atoms in ice, and complex computer models of the core can all be brought together to reconstruct a night sky no human ever wrote about, but many must have seen. If you've stayed with this story all the way to this point, you've done something similar in your own mind. You've taken scattered facts, poles wandering, fields weakening, Neanderthals watching strange auroras, and woven them into a single drifting thread. If you'd like more journeys like this, gentle walks through deep time while you fall asleep, it genuinely helps to let the algorithm know. You can do that quietly by tapping like, by subscribing so you don't miss the next story, and by leaving a comment. If you feel like sharing, tell me where you're listening from tonight. A city apartment, a dorm room, a farmhouse, the cab of a truck pulled over for the night. A country, a region, a corner of the world. It's a way of turning this abstract history into a small modern map of human listeners scattered under one magnetic sky. If you're curious to dive deeper into the hidden chapters of prehistory, bottlenecks, vanished cousins, forgotten climates, I've gathered many of those stories into a book about prehistoric secrets. You can read more about it, and pick up a copy if you like, at sleepytimehistory.com. It's written to be the same kind of companion you're hearing now, calm, evidence-based, and patient enough to fall asleep to. As our story of Laschamps winds down, picture the field itself, slowly regaining its balance. The wandering poles settling into new paths, the tangled multipolar knots simplifying. The dipole growing stronger, like a heartbeat recovering its regular rhythm after a long, strange flutter. Auroras retreating toward the poles. Cosmic ray production easing back toward its usual background hum. The sky looking ordinary again, even though the memory of its strangeness remains, buried in ice, in wood, in stone. On human time scales, these are wild events, a near-vanishing shield, centuries of altered skies, generations living under a field that cannot quite remember where north is. On Earth's own timescale, they are just part of a larger pattern. Reversals and excursions, wanderings and recoveries, playing out over millions of years. The core convects. The field waxes and wanes, continents drift. Climates swing. Life adapts, falters, adapts again. Above it all, the planet keeps turning, day into night, season into season. Tonight, as you lie there listening, the magnetic field is quiet and strong enough. Compasses point north. Satellites orbit inside a familiar cocoon. The aurora hangs mostly over the polar circles. Somewhere far beneath your feet, the liquid iron is still churning, still generating the shield that made this long, fragile history possible. Whatever the field will do in the future, whether it drifts, weakens, or one day flips entirely, it will do so on scales far larger than a single human lifespan. You are catching it in one calm moment of a very long story.